Hello, everyone. Now, this is the last lecture of Machine Learning Summer School 2021. And it is my honor to introduce today's speaker, Professor Michael Bronstein. Professor Bronstein is a professor at Imperial College London and head of graph machine learning research at Twitter. He has served as a professor at USI Lugano, Switzerland since 2010 and held visiting positions at Stanford, Harvard, MIT, TU, and Tel Aviv University. Professor Bronstein is a world well-known leading expert in graph neural network, and his research encompasses a broad spectrum of applications ranging from computer vision and pattern recognition of geometry processing, computer graphics, and biomedical. And his record is really amazing. He was awarded 5 ERC grants, 2 Google Faculty Research Award, 2 Amazon Machine Learning Research Award, Facebook Computational Social Science Award. And actually, the list is pretty long. I can just name a few here. In addition to academic achievement, Professor Bronstein has been the technological lead in multiple successful startup companies. And he previously served as principal engineer at Intel Perceptual Computing and was one of the key developers of the Intel RealSync 3D camera technology. And Professor Stein is also an outstanding speaker. You can find lots of his talks online. I really enjoy his keynote lecture at iClear 2021. I believe you will also enjoy the lecture today. It is very exciting that Professor Bronstein is going to talk about geometric deep learning to us at Machine Learning 2021. Please join me to welcome Professor Bronstein. Professor Bronstein, now the screen is yours.
Thank you very much. It's a pleasure to be here, and well, probably also good to finish to be the last lecture in the school. So I hope not to disappoint. And I will talk today about geometric deep learning. So if you've seen the iClear talk, so this will be an extended version. Or we also gave earlier this summer a course in the African machine intelligence course on the same topic with my collaborators, Joan Bruna, Taco Cohen, and Petr Veličković. So this is a shortened version of the course, so kind of halfway between the two. So what will it be about? If I were to summarize, we'll look at the fundamental principles that underlie deep representation learning and most of modern deep neural network architectures. And if I were to compress it into a single word, the common denominator and common principle that we'll be exploring is the notion of symmetry and how it is manifested differently in machine learning. So symmetry is really, I would say, one of the big ideas that one might want to highlight in science. And here I quote Hermann Weyl, one of the 20th century's most prominent mathematicians, who said that symmetry, as wide or as narrow you may define its meaning, is one idea by which man through the ages has tried to comprehend and create order, beauty, and perfection. And Weyl himself is credited with playing a crucial role in creating the mathematical foundations of modern physics that is based, as we'll see, on these notions in a very fundamental way. And symmetry has really occupied a special place in science, engineering, and arts from the ancient times. You can trace it back to the, for example, Sumerian symmetric designs, or the Pythagoreans in ancient Greece who believed the circle to be perfect to its rotational symmetry. And the term itself actually has Greek origins. Symmetry or symmetria literally translates as same measure, and it was used since ancient times somehow vaguely to convey the beauty of proportion in art and harmony in music. And for example, the disciples of Plato considered the regular polyhedra, what we call the Platonic solids, very fundamental, such that probably the entire universe, the entire world should be composed of these small building blocks. And it was actually not very far from truth. So this is what we now understand in modern crystallography. And the first mathematically rigorous attempt to analyze crystals before actually understanding how matter is structured was undertaken by Johannes Kepler, who is probably known for his eponymous law in astronomy. But he wrote this treatise on the six-cornered snowflake that he sent to his friend as a Christmas gift. And there he came up with a hypothesis that predated modern physics, and this is the foundation of modern crystallography. So the language in which this study operated and that was used was the language of geometry. And geometry also traces its origin to ancient Greece and maybe even before, but at least the early written evidence is from there. And in particular, the seminal work of Euclid, the Elements, that define what we now call the Euclidean geometry, that in fact was the only geometry that we knew for more than 2000 years. And in the core of it, as you know, were the 5 basic assumptions or postulates upon which all this building of Euclidean geometry was constructed. And the 5th postulate about parallel lines was one that defied any attempt to prove it. So it was impossible to prove it. And in fact, it appeared that you cannot prove it. And in the 19th century, basically it marked the end of Euclidean monopoly in geometry. It was quite a remarkable burst of creativity that made geometry into one of the most exciting fields of mathematics at the time. And it started probably with the development of projective geometry by Poncelet, and then Nikolai Lobachevsky, even Gauss himself, that never published anything on this topic, but at least from his notes, apparently worked on constructions in non-Euclidean geometry. Janusz Bolyai, and then Gauss's own PhD student, Bernard Riemann, created an alternative version of geometry where the postulate of parallels or other postulates do not hold. And what happened towards the second half of the 19th century is this remarkable zoo of different geometries, which became a little bit unhealthy situation when mathematicians didn't have a clear idea of how different geometries relate to each other, what actually defines a geometry, and probably had agitated arguments and maybe even hated each other silently, trying to say that my geometry is better than yours. So a way out of this unhealthy situation was shown by Felix Klein. He was only 23 years old when he got an appointment as a full professor at the University of Erlangen, a small city in Bavaria in Germany. And as it was customary and still probably customary in German universities, he was asked to deliver a talk, inaugural talk, where he would present his research prospectus. So actually, this is a legend. So he indeed delivered such a talk, but it was not on the topic of his research, but it was for a general audience about mathematical education. But what entered the history of mathematics as the Erlangen program was a booklet that accompanied this talk, where he outlined his approach to geometry. And the approach was quite radical and a big paradigm shift. So he suggested approaching geometry as the study of symmetry or the study of invariance. These are the properties that remain unchanged under some class of transformations. And according to Klein's mindset, you could define a geometry by appropriate choice of the symmetry transformations. For example, if you look at Euclidean geometry, so you can take a shape and subject it to different transformations, such as translations, reflections, and rotations. And these are rigid motions, so they give rise to Euclidean geometry. And they preserve a lot of things like angles, distances, areas, parallelism of lines, and their intersections. But if you make these transformations more general, for example, if you allow for affine transformations or more general projective transformations, you see that gradually you lose some of the properties. So you get a bigger, what is called a group of transformations, but you get less properties preserved. And Klein himself argued that projective geometry is the most broad form of geometry. Now, I mentioned already that he used the language of group theory to formalize the notion of symmetry and how it acts on geometric objects. And group theory was also a new field of mathematics that was born in the 19th century. The first time this term was used was by Évariste Galois, a French mathematician that was killed in a duel. I think he was only 20 years old. And Klein himself, together with his collaborator Sophus Lee, laid the foundations of what we now know as group theory. So that's why he used a tool that he contributed to developing himself to formalize his notions of geometry. And it really became a very successful program, and that was felt in many other fields of mathematics. So Klein himself actually didn't stay for much time at the Erlangen University. he moved to several places, settling down until his retirement in Göttingen, which was the place for mathematics. That was the university where Gauss himself worked. And many of his colleagues that worked with him at Göttingen took these ideas further, and one of them of particular gravitas was Emmy Noether, who proved that using these ideas of Klein-Erlangen program, that every differentiable symmetry in a physical system has a corresponding conservation law. So this was at that time already. Physicists thought of physical systems as variational problems, where you have some functional that you minimize, and from the optimality conditions of this functional, what is called the Euler-Lagrange equation, you could derive the laws of motion. But the fact that you can derive conservation properties was really stunning, because conservation laws were beforehand completely empirical. So you would make an experiment 1,000 times and you measure very accurately, for example, the energy, and you would say that it's conserved. So here you could make an assumption about some symmetry, for example, symmetry of time, and derive for it conservation of energy. And many other conservation laws, like conservation of momentum and so on, can be derived from appropriate symmetries. And this result is known as Noether's theorem, and it had a dramatic impact on physics. So Weil himself, that I mentioned in the beginning, developed what is called the gauge theory, or the notion of gauge invariance, as an attempt to derive electromagnetism from first principles. He first tried to unsuccessfully unify it with gravitation, the general relativity theory of Einstein. But when the mathematics of quantum mechanics was developed, these ideas were picked up by physicists, and the gauge theories allowed to successfully unify the fundamental forces of nature, again with the exception of gravity. So that was the work of Young and Niels. And in the 70s, this produced what we now call the standard model. That is a single mathematical model that unifies all the forces of nature that we know, again with the exception of gravity. So it is really true, and here I'm quoting Philip Anderson, another Nobelist physicist, that it's only slightly overstating the case to say that physics is the study of symmetry. So if you take a book like this, so I have a book here, which is very nice, it's called Physics from Symmetry. So it derives all modern physics from these basic considerations. Now, what does it all have to do with deep learning, right? So you probably came here to the machine learning summer school to hear about deep learning. So far, I'm bothering you with this boring history of geometry, mathematics, physics, how these things are related. So I think there are two different perspectives. So first, I think the situation that we have nowadays in machine learning reminds a lot the situation in geometry in the 19th century. So on the one hand, of course, nobody has a doubt that deep learning has brought a revolution in data science and made some problems and some applications that maybe a decade ago or 20 years ago seemed borderline science fiction, such as self-driving cars or speech recognition or natural language translation or playing intelligent games like Go, or maybe more recently protein folding. So it had a dramatic impact and completely revolutionized some fields. On the other hand, we now have this zoo of different neural network architectures. Each kind of data has its own architecture, but there are very few unifying principles. And as a consequence, it is hard to understand the relations between different methods, and inevitably it leads to rebranding and reinvention of the same concepts, and also this unhealthy situation and healthy fights about who invented what. So the idea of geometric deep learning is a kind of Erlangen program of machine learning, in the sense that we try to use the same mindset of Felix Klein to derive, to build a mathematical framework that allows us to derive successful neural network architecture. So this is the didactic or the pedagogical use of this framework. And second, of course, you can ask what will be there in a decade from now beyond deep learning. So it is also a constructive procedure to incorporate prior knowledge or inductive bias into your machine learning systems, whether it's neural network or something else that is yet to be invented. So hopefully these principles will outlive their particular implementation, such as backpropagation-based learning. So the term itself, we popularized it in an IEEE signal processing magazine paper that I co-authored in 2017, and more recently a proto book. So this is a book that I'm writing with Joan, Taco, and Peter that we published earlier this year. So it's a 150-page plus long article that eventually will become a book. And you can find more details, including slides and other material on this website, geometricdeeplearning.com. So let us start with looking at the problem of machine learning. And forgive me for maybe this naive example, but more or less we can say that, at least in the simple setting, machine learning is a function approximation problem, right? So if we take probably one of the simplest example of a machine learning algorithm that has to classify images and tell apart between dogs and cats. So you can think of it as a kind of black box, so a known function that we can observe on a training set, right? So we know we can input an image and output a label, whether it's cat and a dog. And we try to find a function from some hypothesis class that fits well the training data. And it will allow us to predict the outputs on previously unseen inputs. And what happened over the last decade or so is the convergence of two trends that made actually deep learning successful. One of them was the availability and emergence of large high-quality data sets, such as ImageNet, which has millions of labeled images. It was a titanic effort by human annotators using Amazon Mechanical Turk. The second trend was the growing computational power, in particular the use of GPUs and the happy match between the architecture of, let's say, convolutional networks and the SIMD, single input multiple data architecture type that is used in GPUs. So together, this allowed to design a rich class of functions that, at least in principle, have the capacity to interpolate such large data sets. And neural networks appear to be a suitable choice to represent such functions, because as we know, even with a very simple choice of architecture like the perceptron, which is probably the earliest and the simplest example of artificial neural network that goes back to the 50s, the work of Frank Rosenblatt, we know that if we connect two layers of such perceptron, basically having just one hidden layer, we have a dense class of functions. Or in other words, we can approximate anything, any continuous function to any desired degree of accuracy. So this is a property that is called universal approximation. Now, the setting of this problem in low dimensions is a classical problem in approximation theory, and it has been researched over the past 100+ years to death, with a lot of results on the error bounds and how many samples and how exactly we need to sample a function to get certain approximation error. But it appears that these results are more or less useless when we need to deal with data in high dimensions. And here is an example. So we can take a very nice, very regular class of Lipschitz functions. And in this example, I'm taking a superposition of Gaussian blobs that are positioned at the corners of a d-dimensional unit cube. And you can see that the number of samples at which we need to sample this function will need to increase when we grow the dimension, and it will depend exponentially on the dimension. So if the accuracy or the error that we allow is epsilon, then the number of samples should be 1 over epsilon to the power of d. So we get a phenomenon that is known as the curse of dimensionality. And unfortunately, this is built into most of the modern machine learning problems, because we need to deal with data that doesn't live in 2 dimensions or 3 dimensions. It lives in 1,000 dimensions, or how about millions of dimensions. So the curse of dimensionality makes a naive approach to learning impossible. So I think there is a question here from Andrea Panizza. I would say more a function learning problem than function approximation problem. Approximation theory doesn't care about learning from data, for example, universal approximation theorem of Sebenko. Well, I think maybe it's a question of semantics. So you try to fit functions from some class. So usually you impose some regularity. In neural networks, this is often done in the form of some regularization. So still the same problem holds for other classes of functions, such as the Sobolev class. So the conclusions are still the same. So probably a good example to look at this curse of dimensionality in action is computer vision problems. Like if we want to classify digits, in this case taken from the MNIST dataset, we see that even very small images tend to be very high dimensional. And if we were to apply a perceptron on this data, we need to vectorize it. So we need to take the geometric structure of the two-dimensional grid and break it into a vector, for example, by column stacking the image. And you see that intuitively we throw a lot of information, because if I just shift the digit by one pixel, I will get a very different vector input to the perceptron. And as a result, we'll need to show a lot of shifted digits to this neural network in order to learn that shifted copies must be classified in the same way. So we typically call this data augmentation. In this case, it will be, of course, a very silly instance of data augmentation, but this is a common practice that is used nowadays in not only in computer vision, but in machine learning as well. So in vision problems, the remedy came from works in neuroscience that analyzed the connectivity of neural networks in the visual cortex, and finding that they're organized into local receptive fields. And this served as an inspiration to the work of Fukushima, the neocognitron architecture that used shared weights that are applied across the image. And actually, in many senses, neocognitron has anticipated the modern version of deep learning, because, for example, it used half rectifiers as activation functions, something that is considered to be almost a hallmark of modern deep learning architectures. And of course, the classical work that really made these ideas work for the first time probably was the convolutional neural networks of Yann LeCun, where this concept of weight sharing across the image effectively allowed to solve the curse of dimensionality and make CNNs invariant to object translation. We'll talk about these concepts in a few minutes in more detail. So let me show you now another example. So this is a graph. In particular, it's a graph that represents a molecule of caffeine, and nodes here represent atoms, and edges represent chemical bonds. And what we want to usually do with these molecular graphs is predict some properties. So if you're designing a new drug, you would like to predict, for example, how well it binds to some target, right? So some binding energy. Or you want to predict, for example, whether it will be soluble in water and can be injected into our bloodstream, or whether it will be toxic, right? And so on and so forth. So this is a very practical and very useful application. So if we were to apply a standard perceptron neural network to this kind of data, you see now that we don't have really a canonical way of shaping our data into a vector. So we can reorder it in many different ways. So we need to address all these possible permutations. We'll see that we'll be using permutation invariance as our geometric prior. And molecular graphs are just one example of graph structured data. There are many other examples. So probably most prominent ones are social networks that represent different relations and interactions between people, different kinds of interactomes or interaction or regulatory networks in biology, graphs with some extra structure, what is called meshes or simplicial complexes in computer graphics, and so on and so forth. So we want to be able to apply deep learning in a principled way on this data, and we also want to somehow formalize the common principles that allow to apply the same model across different types of data. So if we look back at this problem of image classification, which was tarnished by the curse of dimensionality, we see that the situation is actually more optimistic than we thought. And fortunately, we have additional structure that comes from the geometry that underlies the input signal. And we will use this geometry prominently in the following discussion, and we'll call it broadly geometric priors. We'll see that there are very powerful principles that allow to deal with the curse of dimensionality and can be applied in a lot of different problems and different kinds of data. So more specifically in our example, we had images. So images are not just d-dimensional vectors. They are signals defined on some domain omega, which in this case happens to be a two-dimensional grid. So I will denote in gray omega the domain, and I will denote in red x of omega the space of signals that are defined on this domain. Now, this is a linear space, so this is a vector space. The domain itself might not be a vector space. It can be something as abstract as a set or a graph or a manifold, where we cannot add 2 points, but when we define a signal on it, then we can operate with it as a vector space or inner product space. Now, the structure of the domain, its geometry will be modeled by a symmetry group. So if you're familiar with the notion of groups, these are abstract objects that the only thing that you specify is how their elements interact with each other. So the groups exist on their own. But in this case, we are talking about symmetry groups. So these are groups that act on points on the domain. And in particular, in this example of two-dimensional grid, we will assume the group of two-dimensional translations. So an element of the group is something that moves a point to another point. And the action of this group on the underlying grid will be applied to the signal that lives on this grid through what is called the group representation. I will call it ρ, and it can be given by the composition of the group element with the point on the domain and then applying the signal to it. Okay, and just to make things more concrete, if we assume that image is represented as a d-dimensional vector, then the representation of the translation group is the shift operator. It's a d by d matrix that shifts the position of an image. So we have these three structures. So we have the domain that is defined or described by a symmetry group. I should say that the symmetry group is separate from the domain. On the same grid, we can assume different kinds of symmetry. So we can assume, for example, translations. We can assume rotations. We can assume Euclidean motions, which include rotations, reflections, and translations. So there is a question, what is the group here? So the group here is the set of symmetries of the domain. It is different from the domain itself. It can be, in some cases, it can be identified with the domain, but usually it's separate. So on a grid, for example, or in the plane, you can translate, but you can also rotate or reflect, right? Or you can do maybe other things. So the choice of the group actually prescribes the kind of invariance that you will get in the architecture. Okay, so this is our first object. The second object is the space of signals on this domain. So, for example, images, and there the structure of the group or the action of the group is acts through the group representation that I denote by ρ. Okay, and finally we have a set of functions that act on these signals, right? So think of image classifier, for example. It's some black box that inputs an image and produces a label, right? And as we'll see, the properties of the group, we can incorporate them into this black box in the form of invariance or equivariance. So let's make things more concrete. So if you think of a problem of image classification, I want to say that this is a cat no matter where it's located in the image, right? So we want such a function f that acts on an image that if I shift the image by some group element g, right, or by the representation ρ of g, then the output of the function will not change. So we're talking here about group invariance, or in this example, shift invariance, right? So the output is unaffected or invariant under translation. Another possibility is when the structure of the input and the output is the same. So you can think of a situation when I want my neural network to label the pixels in the image, for example, to segment background from foreground or detect the cat in the image, right? And in this case, of course, I want the output to be transformed in the same way as the input. So if I shift the input image, I want the output mask to be shifted in exactly the same way. So I should say that the input and the output structure is not necessarily the same. The number of dimensions, for example, can be different, right? So there is no necessity that this representation is exactly the same. So the group will be the same, but the representation might be different. So this is an illustration of how an invariant representation will look like. So if you think again of our problem of handwritten digit or letter classification, so here we have different styles of the letter A and B, and we also have different transformations that are applied to these letters. So we have different rotated versions of two types of A's and two types of B. So you can imagine a neural network where first we'll be able to undo all the possible rotations, right? So we'll be able to create an invariant rotation invariant representation. And then we'll have some maybe additional layers that will identify different styles of A and tell them apart from B. Sorry, there is another question. What happens when the shift makes the signal cross the boundaries of the domain? Yeah, so well, you need to assume some boundary conditions. Okay, so I will talk about it later. So you typically assume some boundary conditions. So it's easy to assume, for example, periodic boundary conditions, right? So if it's if the image partially disappears, then of course you cannot model it in this way. Okay, I will talk about it later. So the problem with this approach, of course, is that at least in computer vision and image analysis, if you have a complex object or a complex scene to reason about it, to recognize it, you need first to analyze its parts. And what happens is that relative positions of parts are important. So I'm quoting here Hinton, but it was probably observed way before in computer vision literature. And if you insist on having intermediate representations that are invariant, for example, to rotations, then you might end up with this situation that you have each part rotated independently. And of course, overall, the result makes no sense. So you lose the important information about relations between parts. So you really need to use equivariant representations. And this is how typically convolutional neural networks and other architectures as well are structured. So you have a sequence of equivariant layers, like convolutional layers, and then maybe, for example, your task requires an image classification. You have a global readout, pulling a fully connected layer that produces a single output for the entire image. And actually, it's important to realize that convolutions are not invariant, they are equivariant. So if I take a digit 3 and I apply to it some filter, I convolve it with some small kernel, I will get the shifted version of the input, right? So it changes in the same way as the input. Now, you can also apply these ideas to other types of transformations. So here's an example of rotation. And if you look at CNN, if I rotate the input, there is no reason whatsoever that the output will be equivariant with respect to rotation. And indeed, it's maybe hard to see it in the feature map. You see that it rotates and something changes there. So if I stabilize this view, you will see that the feature maps are deformed. So you need some different architecture that is equivariant to rotations, and there are such designs. So this is group equivariant CNN, and you can see that in this case, the output changes exactly in the same way as the input. Okay, and another way maybe to think of equivariance is a kind of symmetry consistent generalization. And here what you see is two images, right? Let's call them X and X prime, that undergo some transformation. So what is shown in gray here is an orbit that is associated with these group elements. And let's say that we have a representation of this group that I call rho 1 in the input space that rotates these images, right? So let's say that I have some function that would I ideally want to identify these two different styles of the letter A, right? So in the feature space, I want f of x to be equal to f of x prime. So what equivariance rules out is this kind of situation, right? Well, for the rotated versions, I will have two different representations. So it forces us to have this form of consistency. And in this case, as I mentioned, the representation of the group in the input and the output space doesn't need necessarily to be the same, because the dimensionality and the structure of these spaces might be different. Now, to the question that was asked before, what happens, for example, if the object moves around outside of the image? So I have a slightly different example. So imagine that I have a video, and here are two frames of the video. So I have two cars, one moves left and another one moves right. So we don't have a global translation that explains the relation between these two images, right? Locally, we can describe the motion of the red and the blue car as a shift, but globally there is no single shift that explains it, right? So that's exactly the kind of situation. So a more appropriate model here would be some form of warping or domain deformation. So in other words, we have an automorphism, a map from omega to itself that somehow moves the pixel. So we will assume that it's a bijection, and if we compose it with the image, we will get some kind of warping, right? Like in the case of the car. So we'll assume that it's smooth, differentiable, right? And the action of this warping can be represented by a linear operator that I will denote as L with subscript tau. So if you look at this bigger space of automorphism, so first of all, it's also a group, right? With respect to function composition, if I compose two bijections, I will get a bijection. But we are interested in a subgroup of it, which is the subgroup of translations, right? And if I have, for example, an image and a shifted version, we know that these are described by elements of the subgroup. Now, if I have a warped version of the house, I don't get a translation. I cannot describe the transformation from here to here by a translation, but I want to measure, to describe that it's sufficiently close, right? Because this distorted house looks like a shift with maybe a little bit of extra, right? So I need to be able to measure some metric or some distance between this more general deformation and an element of the group. And this allows us to generalize the exact notions of invariance and equivariance. We call it geometric stability, and we say that a function f is geometrically stable if this kind of result holds, right? If we can upper bound the difference between f applied to x and the transformed version of x. And we express it with, for example, using the Dirichlet energy that tells us how smooth this deformation field tau is. And this was a result that was shown by Joan Bruno with Stéphane Mallat, and they applied to the analysis of scattering transformations and convolutional networks, showing that convolutional networks are not only equivariant, but they're actually stable under something that doesn't look like exact shift, so local smooth deformations. This is what makes them powerful. Other representations, for example, Fourier-based representations are not. So that's why you need multi-scale analysis such as wavelets or scattering representations. And you can see that this is a generalization of shift invariance, because in the case of shift, this tau will be a constant displacement, advection, and the gradient of tau will be equal to 0. So another type of geometric prior is called scale separation. And in some cases, we can construct a hierarchy of domains, for example, by coarsening the grid. So I denoted by omega wave. And this coarsening creates also a hierarchy of spaces that live on this hierarchy of domains that are related by what is called coarse graining operator that I denote by P. And we can take our function f and construct a coarse scale version of it. So again, think of image classification. I can take my image, I can downsample it and apply a classifier at the lower scale. So we can say that our function is locally stable if we can approximate it by the composition of the coarse scale function and the coarse graining operator, right? So if I can take, for example, my image, I can downsample it, apply the coarse scale classifier, and the result will be similar to what I would get if I apply the classification at the fine scale, right? And this is actually a very powerful principle that is also commonly used in physics. So if you're familiar, for example, with fast multiple methods, it exploits exactly this principle. And this is also what is exploited in multi-resolution signal analysis, such as wavelets or similar methods. So if we combine these two principles, we get this very general blueprint that we call geometric deep learning, that hopefully you can recognize in probably 99% of popular deep neural network architectures. We typically have a sequence of equivariant layers that preserve the structure of the domain, and then maybe a global pooling layer. And in some cases, we can also have a hierarchy of domains that are produced by some coarsening procedure that takes the form of local pooling. Like in convolutional networks, you downsample the grid and you apply some typically nonlinear operators such as maximum that are interleaved with the equivariant convolutional layers. And this principle, it is very general. You can apply it to different types of geometric structures, and this is what I will try to describe next. So in particular, we'll be talking about grids. We'll be talking about homogeneous spaces where there are global symmetry structures, where the groups act transitively. We can talk about manifolds, where there is local invariance and equivariance, or graphs of which grids can be seen as a particular setting. And we'll show that the implementation of these principles gives rise to very popular architectures such as CNNs, deep sets and transformers, graph neural networks, different intrinsic mesh CNNs. I will not talk about LSTMs, but we can also derive them from considerations of time warping transformations. So they are all particular instances of this broad geometric deep learning blueprint. that is obtained by choosing the right domain and the right symmetry group. Another question from Andrea. Local pooling will be a scale separation prior inductive bias. Yeah, that's correct. Local pooling is a scale separation prior. It's one instance of it. So one thing that I already mentioned, and I would like to emphasize here again. So typically the symmetry group is different from the choice of the domain. So again, if you think of image analysis problems, so imagine that you have a self-driving car and the task is recognition of traffic signs. So typically the traffic signs are straight, right? They are vertical. So in this case, probably, at least with some simplification, you need to deal only with translation symmetries, right? So it's you can assume that the domain here is a grid and the group is a translation group in 2 dimensions. If, for example, imagine that I have an airplane that doesn't only stand on the road, but can also rotate in different ways, then I need to deal with translations and rotations. But I don't have reflections, right? Because they are not physical, unless I look at my traffic sign in the mirror. But if, for example, my application is analysis of histopathological samples, where I take a small slice of tissue and put it under the microscope, then reflections are very natural because I can just flip the glass and I will have it in addition with translations and rotations. So it really depends on the application. You need to use some prior knowledge about your problem to incorporate the correct structure. Yeah, so another question from Tom. How can we find what symmetries apply to a given domain? And if we don't have intricate domain knowledge? Yeah, I'm often asked this question. So there are some attempts to discover symmetries from data. You can think, for example, of architectures such as transformers that to some extent do it, but this is an open question still. Yeah. Okay. Yeah, another question. As an extreme case, if invariance is required under the symmetric group of the grid, what would the resulting architecture need to be? Well, so it might be something quite boring, right? So one example would be an operation that is invariant to translation, and maybe even more general transformations, just sum or average all your pixels, right? So this is obviously invariant to translations, but it's not very interesting. So maybe a more realistic application, take the Fourier transform, and then shift becomes a complex phase. And if you take the absolute value, you get rid of the phase, and this gives you a translation invariant representation. The problem is that it's not geometrically stable. So if I have something that looks almost like a translation, but for example, I allow to deviate a little bit from the translation group, then this thing falls apart. You will get different components in all the frequencies of the signal. That's why when dealing with these such representations, people have preferred to look at something like wavelets, where you have the multi-resolution structure. Okay. What are your thoughts on 1D convolution versus LSTMs for time series application with respect to symmetry? Yeah, good question. So LSTM, as we show in the book, I don't have time to go into it today. You can express it as time warping transformation, so it's more general than just translation. So that's why it is probably better. Okay, so let's talk about graphs. Why we are interested in graphs? We really find them ubiquitously as a generic model that allows to describe practically any system of relations or interactions. I should say pairwise relations and interactions. And you can really see graphs used to model, for example, molecules at microscopic scales, interactions between different molecules, such as interaction networks in biology, or maybe at the macroscopic scale of the entire planet, we can model interactions between people as social networks. So this is actually a good metaphor to use, and we can think of a social graph or a social network as a graph where the users are nodes, their social relations are edges, and we can think of situations when we have these edges, which are pairs of nodes, ordered or unordered, right, or directed and undirected. So if you think of friendship relations, it's likely that it will be symmetric. So if I'm a friend of somebody, then somebody is a friend of me. So this is an undirected graph. Or if it's, for example, follow relations, like on Twitter, I might follow some important celebrity, but most likely this celebrity wouldn't follow me, right? So this is directed edge. And we can also attach some features to this graph. So we can attach it in the form of node features, which we'll model as d-dimensional vectors. And for simplicity, let's assume that we don't have any features associated with the edges. So one thing that you need to understand about graphs is that graphs are abstract topological objects. And what I do here by numbering the nodes of the graph, this allows me to represent the features as a matrix. So I take the feature vector of the first node and put it as the first row of the matrix, of the second as the second row, and so on. And I can also model the structure of the graph in the form of adjacency matrix. So it's n by n matrix, where n is the number of nodes. And I have a 1 in the position ij if there is an edge between I and j, and 0 otherwise, right? But of course, this numbering of the nodes is completely arbitrary, right? I could reorder the nodes of the graph like this, right? I can exchange, for example, the first and the second one. So as a result, the feature matrix will be changed, and the adjacency matrix will be changed. I can completely scramble it. So really, this is defined up to a permutation, right? So permutation matrix P. And you can think of permutation matrix as a representation of the permutation group of n elements. We have n factorial possible permutations. And you can also see, this is maybe a slightly subtle technical detail, that for different objects, we have different representations, right? So this is what we would call raw in the notation that I used before. So you see that on vectors, it acts differently than on matrices. If I have a vector, if I'm permuting the rows of the feature matrix, I act on it with P from the left. But if I need to permute a matrix, right, if I need to permute rows and columns, I need to act on it by P from the left and by P transpose from the right. Okay, so you see that it's the same group, but different representations because we have different structures. Now, what we are interested in graphs is computing functions that input graphs and features on the graphs and output something. And let's say that the application that I mentioned, predicting a property of molecules, so this will be a graph of, let's say, caffeine molecule with some description of the atoms, right, that is given by X, the node features, and A describes the structure of the graph through the adjacency matrix. No matter how I order the nodes, we don't have a canonical order, I want the output to be the same, right? So the binding energy that I output, for example, should be the same. So in this case, we want to be the function to be permutation invariant, right? And this is what it means, that I can permute the input and by applying P to the feature matrix X and P transpose to the adjacency matrix A, the result will be the same. Okay. Now, if I have a task that requires node-wise labeling of the graph, like, for example, I want to detect some bad users on a social network, I want the output to be reordered in the same way as the input. So if I call the gray node 1, it will appear in the first position in the output vector. If I call it 5, then it will appear in the 5th position of this vector. Okay, and you can also think of it as intermediate layers in our neural network. So remember the general blueprint, we had first a sequence of equivariant layers that are followed by an invariant layer. So this would be a way of constructing intermediate feature maps on the graph. Okay, so the output is permutation equivariant. And this is how a typical graph neural network architecture will look like. You hopefully will immediately recognize it as an instance of the geometric deep learning blueprint, where we have the permutation group as the geometric prior and that acts on the graph. And we have a sequence of permutation equivariant layers, possibly a permutation invariant readout, and possibly some intermediate pooling layers that coarsen the graph. And in some works, this can also be done in a learnable way. So you learn how to coarsen the graph. Now, actually, graph neural networks are not that new, even though they became very prominent and very popular in the past several years. Probably the first works date back to Alessandro Sperduti on recursive auto-associative memory, paper from 1994. And the term graph neural network actually appeared in a series of papers from the group of Marco Gori from the late 2000s. And probably the reignition of the interest in this field was from the work of Jean Brunner from 2013 on spectral graph CNNs. that was already in the modern era of deep learning, and I will talk about spectral representations of graphs and manifolds as well. Now, if you ask people that work on graph theory, they would say that actually graph neural networks are a fancy name for a graph algorithm that is used for graph isomorphism testing, that is called the Weisfeld-Lemon test, and it was shown actually quite some time ago, more than 10 years ago, that essentially you can compute descriptions of graphs by refining the colors. So this was a famous paper of Weisfeld and Lemon from the 90s, where they tried to solve the graph isomorphism test, determining if two graphs are the same up to reordering of their nodes by color refinement scheme. And they initially thought that it is a polynomial time algorithm for solving this problem. And actually they showed it for small graphs up to 9 nodes. And then a year later, a counterexample was found with a bigger graph. And actually for many years, it was not even clear what is the complexity of graph isomorphism testing. We knew that it's not NP, but it was usually put into its own complexity class. And only recently, I think Babai showed that it can be solved in quasi-polynomial time. And it is also interesting that to Weisfeld and Lemon themselves, the problem was posed by a chemist named George Vladuc. And he probably deserves the credit of being the first to model molecules as graphs as early as 1963. And I think in the West, it is Morgan who is credited with the so-called Morgan molecular fingerprints. That was a paper from 1965. And what Vladuc was asking Weisfeld and Lemon to do is to devise an algorithm that would allow to distinguish between different molecules. And it's actually interesting that there is a parallel universe or parallel thread of works in chemistry that are surprisingly similar to graph neural networks. And it's interesting to look at these papers. So for example, if you look at the paper of Baskin from 1997, he describes a neural device for searching correlations between structures and properties of organic compounds that would be invariant with respect to the numbering of atoms in a molecule. That's what we call permutation invariance. And they used an architecture that is analogous to biological vision systems. So that was a graph convolutional network. And that was 25 years ago. It will take another 15 years for deep learning to become the big thing that it is nowadays. So there is another question. What do you mean by blueprint? So what I mean by blueprint is a kind of overarching principle where you make certain choices and you get different architectures. So what I try to describe. Another question regarding chemistry: aren't molecules with some geometrical structure or at least physical constraint in the topological form it could be in? And if so, wouldn't taking them as geometry-less graph be disposal of something that could be used potentially as an inductive bias? Yeah, you're completely right. So molecules indeed are what is called geometric graphs. So they do have their topological structure, but they also have some geometric coordinates. So they're embedded in R3, right? So it's actually interesting that many molecules, or almost all molecules, or a large number of molecules, are planar graphs. So you can draw them in 2D, and then it is interesting actually to talk about the Weisfeld-Lemon dimension, that in this case, they can all be resolved by the classical WL test. But in this case, what you would do, you would treat separately the chemical features from the geometric features, and this can be done in the form of equivariant message passing. So this is actually the algorithms that are now being used successfully for predicting properties of molecules, and this was also a form of equivariant message passing was used in the AlphaFold 2 by DeepMind for predicting folding of proteins. So if you have time, I will talk about it later. Okay, so let's look at how the core of graph neural networks look like. So the core operation of a typical GNN consists of local aggregation. So we take a node, we look at the neighbors, so nodes that are attached by edges to this node, and we look at their features. And now here there is some technical subtlety that even though the neighbors, their indices are unique, their features might be repetitive, right? So in this example, I have the red node has 5 neighbors, but 2 of the neighbors have the same features, this bluish one, right? So together they form what is called a multiset. So it's a set where the same element can appear more than once, denoted by double curled brackets. So what we need to do is we need to aggregate these features together with the feature vector of the node itself. And here I remind you that we don't have a canonical ordering of the neighbors, so we need this aggregation to be permutation invariant. Now we can apply this aggregation at every position in the graph. So this architecture obviously doesn't care about how many neighbors each node has and how many nodes are in the graph. It is also potentially at least mappable to efficient architectures, maybe not GPUs, but other architectures that have this mindset of looking at the neighbors of a node in the graph. And then if we compute these features in this way at every node of the graph, we get a matrix of node feature vectors. And this function will be permutation equivariant. It's easy to show that each row in this matrix will be obtained in a permutation invariant way, right? So it's invariant to the reordering of the neighbors. But if I permute the order of the nodes, then the rows in this matrix will be permuted accordingly. Okay. Now, there are multiple ways of how this aggregation operation will look like, and here is a typical example. So typically we'll have some symmetric function that acts as an aggregation operator. Typically it's a sum or a maximum. We'll have a learnable function that I denote here by psi and phi that transforms the neighbor features. And well, the function phi in this case transforms the aggregated features to update the features of node I. Okay. Now, of course, there are a lot of nuances and differences in how different architectures implement these functions. So it is probably pedagogical and convenient to distinguish between three broad classes of architectures that probably encompass 99% of GNN models. So the first flavor is convolutional, and this is how some of the first works on graph neural networks look like. And in this setting, we aggregate neighbor features, weighting them by some structural coefficients, Cij, that depend only on the structure of the graph. So you can think of them as a kind of importance or the contribution of node J to the representation of node I. We'll see in a few minutes that in the case of grids, it boils down to the classical convolution. Now, the second flavor is based on attention, and in this case, the aggregation coefficients now depend not only on the features themselves, but also on, not only on the graph, but also on the features themselves. And probably the most popular instance of this architecture is graph attention networks, or GATT, a paper by Petar Veličković from DeepMind. And probably the most general flavor, we have a general nonlinear function that depends on both xi and xj, and its output can be regarded as a message that is sent from node j to update the node I. So these graph neural networks are called message passing. And in chemistry applications, they were introduced by Justin Gilmer from Google. And that's why, as I said, a lot of the work in this field was motivated by predicting properties of molecules, problems from chemoinformatics. So it is also interesting to talk about special cases of graph neural networks. And if we take a graph and remove all the edges, we get the set, right? And the set shares the structural property of graphs of being unordered. We don't have a canonical way of ordering the elements of a set, typically. So in this case, we can do two extreme solutions. The first would be to treat each node completely independently from the others. So in this case, we can apply a shared function phi to the feature vectors, and this will be, the result will be a permutation equivariant function over the set that is a special setting of the convolutional graph neural network where we have an identity adjacency matrix. Okay, and if you're familiar with the deep set architecture, so this is what it is. So there are two concurrent papers they called deep sets and point nets. So point nets is the same idea used in computer graphics that was developed for the analysis of 3D point clouds. Now, in another extreme, you can assume that every node can interact with any other node. So this can be represented by a complete or a fully connected graph. And in this case, you can actually see that if you try to apply the convolutional flavor, it makes no sense because the second argument of this function will be the same for every node. So we need to upgrade it to at least the attentional flavor. And you can interpret in this case the attention as a form of soft learnable adjacency matrix. And I hope you can recognize the transformer architecture that is now predominant in NLP applications. You can see that it's also a special setting of a graph neural network, right? So here, this is a little bit of cheating because, of course, as you know, transformers are applied to text sequences, and in sequences, we don't have this arbitrarity in the positions of the nodes. We actually have some order that comes from the sequential structure, and typically this node positional information is provided in the form of what is called positional encoding. So we have additional features that allow to uniquely identify the node in the sequence. And similar ideas of positional encoding have also been applied to graphs. So there are many flavors. One of them that I'm describing here is what is called graph subtraction networks, where we use the counts of simple graph subtractions such as cycles, clicks, triangles, and so forth as a structural descriptor. And here probably what is important to say is that you always have a trade-off between expressive power and generalization, right? So in the extreme case, you can say no positional encoding, so the message passing function does not distinguish between nodes. So it is always the same at every location in the graph. At the other extreme, you can say that I produce random features for each node, and then the message passing function is unique for every node, right? It can perfectly distinguish between different nodes. The problem is that usually I want to train my network on one set of graphs and apply it to another set of graphs that I have never seen before. And good luck to reproduce random features in the same way on a different graph, right? So you need something that is, on the one hand, expressive, on the other hand, is generalizable. And that's why the structural description is a good halfway. So we can show, for example, that it's strictly more powerful than the Weisfeier-Lehmann test. So it's more powerful than message passing algorithms, even though it has the same structure of a message passing network. It just has a pre-computation step of providing these structural descriptors. And you can think of it as a form of problem-specific inductive bias. And here is again an example from the domain of chemistry. So in organic chemistry, molecules have a lot of ring-like structures. So if you look again at this molecule of caffeine, it has a ring of size 5 and a ring of size 6. And you often find what is called aromatic compounds, which have benzene rings. So this is a very prominent motif in molecular graphs. So what we show here is that if we count cycles of length 5 or more, or 6 or more, we get significant boost in predicting the properties of these molecular graphs. In particular, here we are looking at water solubility. So the prediction error decreases dramatically. So it is a form of problem-specific inductive bias. For example, in social networks, you often find that cliques are prominent and important structures. So I hope to have convinced you that even in the cases where the graph is not given, as an input, graph neural network still makes sense, right? So you can assume that the graph is fully connected and learn the right one that you need for your problem. So there is a question: can you re-explain briefly the graph subtraction network and why they have more representation power than GNNs? Okay, so the graph subtraction network is exactly a graph message passing network where as positional encoding, so we have an additional piece of information that comes to the message passing function. We describe the number of times a node or an edge, depends on the version, appears in some structure. So I count, for example, in how many triangles locally a node participates, or in how many clicks. And what you can show, this is shown by counter examples, that, for example, the Weisfeier-Lehmann algorithm cannot count triangles in graphs. And if you count triangles and provide them as structural descriptor to a message passing architecture, you can count triangles. So typically the examples where the Weisfeier-Lehmann algorithm fails and the message passing architectures are equivalent to the Weisfeier-Lehmann algorithm are strongly irregular graphs. So you can take an example of strongly irregular graphs where one of them contains 4 clicks, another one contains triangles. This is what we show in our paper. And if you count 4 clicks, then you can distinguish between these two graphs. On the other hand, you need to go to a higher order or higher dimensional Weisfeier-Lehmann test in order to do it. So another question: is there a way to map a set of graphs in learnable way with respect to a task-related objective, for example, for the sake of drug discovery. Yeah, well, this is essentially what graph neural networks try to achieve, right? So you can think of the last layer of this representation as being a vector that describes the graph or the features that you have on the graph, and then of course how this space is structured depends on the task. So if you want, for example, to predict I don't know, toxicity, it will probably be different from if you want to predict some binding energy. So in many cases, we can actually pre-train the network on some chemical tasks, and then it generalizes reasonably well for other tasks. Same way as you can, for example, pre-train a convolutional network on ImageNet and then use this pre-trained network, for example, in the reconstruction of the event horizon of the black hole. I think this is what was done. So it was standard CNN that they used. Okay, so shall we make maybe a 13 minutes break here?
Sure. So we take a 30 minutes break. Okay.
Yeah,
so
and we reconvene at.
Yes.
Yeah, reconvene in 13 minutes. So my time it will be 2:20.
Yes. So it would be 9:20 at Taipei. Yes. Thank you.
Wonderful. Thank you.
Thank you.
Excellent. Thank you very much. So let's continue. So maybe first there is a question. You mentioned in the case where graph connectivity structure is not given as in transformers, the connectivity structure is learned from the features, but aren't the information from the adjacency matrix supposed to be complementary to information from features? In other words, for example, would one be able to learn a molecule structure from features of atoms? Yeah, so it's a good question. So in some cases, you don't have a graph, but you can assume that there is some latent graph that comes from the structure of the space where the nodes of this presumable graph, right, or elements of the set are located. In other cases, and this is what I'm describing in this slide, you might be given a graph, but you don't want to stick necessarily to this graph to do the message passing. So you have some form of decoupling of the computational graph from the input graph. And there are multiple shapes that this can take. So it can take the form, for example, of graph sampling, right? So if you have a graph where you have very high degrees for some nodes, like in social networks where you have very popular users, you cannot, of course, collect messages from a million of nodes, so you need to sample. Another possibility is to rewire the graph, and there are multiple approaches that do it. Or maybe instead of looking just at the neighbors, you can look at the neighbors of the neighbors. So you use what is called multi-hop filters. And you can also make the graph on which to run the graph neural network learnable and optimize it for the downstream task. And that's what is called latent graph learning. So in a sense, transformers are a way of doing it. And you can also change the graph throughout the layers of the network. So you can make it differential and backpropagate through it. And this way the graph can be updated between different layers. And we did an architecture with colleagues at MIT called dynamic graph CNNs for the analysis of point clouds. And probably this is a good example why you want to update the graph between different layers. So here we have a point cloud in 3D, and the task is segmentation. So you want to segment, for example, this point cloud of an airplane into the body, into the engines and the wings. So we start with a graph as a kind of coarse and crude representation of geometry to make it easier for the information to flow between the different points on the cloud. But as you go deeper into the network, the features that are associated with these points become increasingly less geometric and more semantic. So you see that, for example, in layer 3, you have nodes that nicely separate the different engines. So in this case, you want the features capture more semantic information, and you want to the flow of information to be coordinated with that. So you want to connect semantically similar points. And the most primitive way to do it, as we did, was nearest neighbor graph in the feature space. We had a follow-up paper where we had two separate spaces, one used to define, to construct the features that you will be diffusing on the graph by message passing, and another space is from which the graph is constructed. And maybe in some perspective, these latent graph learning methods can be related to manifold learning or nonlinear dimensionality reduction, which built on the premise that even though your data might be of extremely high dimension, its intrinsic dimensionality, or somehow the number of degrees of freedom that can explain the variability of the data, is low. And the typical metaphor that is shown is this Swiss roll example. So you can think of your data at least approximately as if it was sampled from a manifold that is embedded in a high dimensional space. So in this case, the manifold is 2-dimensional, but the space is 3 or more dimensions. And you can capture the structure of this manifold in the form of nearest neighbor graph that you would then embed into some low-dimensional space where it would be easier to do some machine learning tasks. Typically, it was clustering. And the reason why these methods never really worked in real applications is that these 3 stages are completely separate. So you first build the graph in some way, right, on some representation of the data, then you compute the embedding, and then you apply the machine learning. But of course, it's clear that the way that the embedding will look like hugely depends on how you construct the graph, right? And the result of machine learning will hugely depend on how the embedding looks like. So with latent graph learning, graph neural networks, you can build everything into a single pipeline where you have an end-to-end process where you learn both the graph and the filters operating on this graph. Okay, so if there are no questions about graphs, let us move to grids. And grids are obviously a particular kind of graphs, right? And again, somebody asked about boundary conditions. So let's assume that we have periodic boundary conditions. So basically everything is defined modulo n. So this is called a ring graph in graph theory. Okay, and one thing that if you compare to a general graph that happens on the grid, that the structure of the neighborhood is exactly the same, right? We always have two neighbors. Now, I remind you that on a general graph, what we did to compute a function on this graph, we had to aggregate our neighbor features. And because we didn't have a canonical order, we had to work with some symmetric or permutation invariant aggregation of this multiset, right? But of course, on a graph, on a grid, we do have an order of the nodes. So we don't need this symmetric aggregation. We can do a different form of aggregation. So now we can order, for example, first the green, then the red, and then the blue. And if this aggregation function is linear, then we get the traditional convolution, right? So if I were to write it as a matrix vector multiplication, we have a matrix that has a very special structure. So it has multiple diagonals, and the element on each diagonal, the elements are the same. We call such matrices circulant, and they're synonymous with convolution. So it's just another way or another name for convolution, or technically this is what is called circular convolution because of the periodic boundary condition. And they construct the circulant matrix by taking a vector of parameters that I denote here by theta, right, a column in this matrix, and just cyclically shifting it and appending shifted copies of this vector forming this matrix. Okay. Now, these are very special matrices with nice, particular, and remarkable properties. And one of them, for example, that they commute with respect to multiplication. So typically, we know that for matrices, AB doesn't equal BA, right? So matrices are not commutative. But in this case, circulant matrices do commute. And in particular, they commute with a very special kind of circulant matrix, which we call the shift operator. It cyclically shifts the elements of a vector by one position. So remember when we talked about representation of the translation group, and we said that we have a D by D matrix that does the shift. So that's what it is. This is how it looks like. Okay. Now, saying that circulant matrix commutes with shift is just another way of saying that convolution is shift equivariant, right? So we can first apply convolution and then shift, or vice versa. The result will be the same, right? And sometimes in signal processing books, it is called shift invariance, but the correct term is shift equivariance. Now, this property also works in the other direction. Not only every circulant matrix commutes with shift, but also every matrix that commutes with shift is circulant. So we can define convolution by this property. So in other words, convolution is the only linear operation that is shift equivariant, and it automatically emerges from this assumption of translational symmetry. So I hope you can see the power of this geometric deep learning approach, or our blueprint, that we start with the domain, we make an assumption about the group, and we get convolution automatically from this assumption, right? So it's not just a formula that you get out of the blue, you get it from the very first foundational principles. And if you're familiar with representation theory, you will find that this is a particular setting of a broader concept. Now, here's another interesting thing. So we know from linear algebra that commuting matrices can be jointly diagonalized, or in other words, in this case at least, there exists a common basis of eigenvectors, which you can think of it as a kind of change of coordinates, that in these new coordinates, the action of the convolution amounts to pointwise product. So in other words, it becomes a diagonal matrix. These diagonal elements are called eigenvalues, right? So different convolutions have different eigenvalues, but the same eigenvectors, right? And because we do this analysis, actually, because all circulant matrices commute, we can pick up one of the matrices, and we know that the eigenvectors of this matrix will be the same as the eigenvectors of any other circulant matrix. And it's convenient to look at the eigenvectors of the shift, which we can compute by hand. And surprisingly, these happen to be the Fourier transform, the DFT, the discrete Fourier transform. So all convolutions are diagonalized by the Fourier transform. And the eigenvalues are given by the Fourier transform of the vector of parameters theta from the circulant matrix. So you see that the Fourier transform also emerges from the fundamental principle of translational symmetry. And again, if you're familiar with representation theory, this is what is called the irreducible representations. And I hope you can see here the famous duality between doing convolution in the spatial domain, right, by sliding window or application of a circulant matrix, or doing first the Fourier transform and doing element-wise product in the Fourier domain, right, and then doing the inverse Fourier transform. And this is actually has been bread and butter of signal processing for nearly 50 years, because in the Euclidean case on grids, the structure of the Fourier transform, this basis has redundant structure, so it is possible to compute it in n log n operations using one of the fast Fourier transform algorithms. Unfortunately, we don't have this luxury on more general domains. So again, we could have picked up here any matrix, right? And we picked up the shift operator and obtained the Fourier vectors, the Fourier basis size eigenvectors of this matrix. We could pick up any circulant matrix or any convolution, for example, the Laplacian operator, right? And the eigenvectors will be the same. So this is actually the starting point of how you can do spectral convolution on graphs, because on graphs you can define the Laplacian. There is no immediate analogy of the shift operator. Well, you can use the adjacency matrix as an analogy of the shift, and the results will be slightly different. So obviously there is no complete analogy of commutativity, but you can still interpret the Fourier basis as the Laplacian eigenfunctions, right? So in one-dimensional continuous setting, the Laplacian is just second-order derivative. So take second-order derivative of the complex exponential, right? The basis function of Fourier, and you get the same function multiplied by the frequency squared. You can also interpret the Fourier basis as the smoothest orthogonal basis, right? It minimizes what is called the Dirichlet energy, the quadratic form that is given by the Laplacian. And you can also interpret it as local difference from neighbors. So if you discretize the Laplacian on a grid, you see that you take the sum of your neighbors to the left and to the right and subtract from it twice the value of the function at the node I itself, right? So basically it measures how different you are from your neighbors, and the Dirichlet energy is a global way of measuring how different the signal is from its local environment, so some form of smoothness. Right, so on the graph, you can write the Laplacian in exactly the same way. So you can write it as a weighted sum of the differences between the feature at node U and the neighbor node V in the neighborhood of U, right? And if I slightly rearrange this formula, you get it that it's the feature at the node U scaled by the degree, right? And some weighted average or weighted sum of the neighbors. So again, it's the difference of myself from my neighbors. And you can also see that this is a special linear form of this local permutation invariant aggregation, because sum is a symmetric function. It doesn't matter in which order you sum, you get the same result. So this is the permutation invariant aggregator that we called phi in the previous discussion. Another question from Andrea: is this equivalent to say that the Fourier transform of the convolution of an image with the filter is simply the product of the respective Fourier transforms? So this is correct. Well, any signal, right? So any grid, it can be a two-dimensional grid or a one-dimensional grid. So with two-dimensional grids, the Fourier transform is actually obtained as a tensor product of one-dimensional Fourier transform. So, but it's easier to see with one-dimensional case. Yes. So short answer, yes, that's the case. So there is also a convolution theorem for multi-dimensional Fourier transforms. Okay, so this is a linear permutation equivariant function. So if I multiply my feature matrix by the Laplacian, I get a permutation equivariant function. It will be reordered in the same way if I reorder the nodes of the graph. And this idea was used in the paper that I mentioned by Joan Brune. I should say that it has been used way before in the computer graphics and geometry processing community, back in the 90s. And the idea is that if we have an undirected graph, you can take the graph Laplacian. It's a symmetric matrix, so as a result, it has orthogonal eigendecomposition. So you can take its orthogonal eigenvectors, I denote them here by phi, as the analogy of the Fourier basis, right? So the Fourier transform will be just projection on this orthogonal basis. So again, some form of orthogonal change of coordinates. So you rotate your system of coordinates. Unfortunately, we don't have FFTs in this case, so the complexity of this computation will be n squared. We need to multiply a vector by a dense matrix. we should also say that the computation of the eigenvectors will be almost n cubed. So this is pretty expensive. So this is already the first disappointment. Inverse graph Fourier transform is the same multiplication by phi instead of phi transpose. And then we can define spectral convolution as the pointwise product of the graph Fourier transforms. And sorry for the mistake, it should be n complexity, not n squared. So overall complexity is n squared, and this is not good. Another thing that is not good is that the filters that are obtained in this way in the spectral domain are not necessarily localized on the graph. And finally, it appears to be unstable to perturbations of the domain. If I slightly change the graph Fourier transform can change a lot. So the Fourier coefficients is hard to generalize them, right? I described the filter as by its Fourier coefficients. So if I learn some set of coefficients on one graph, I cannot immediately transfer them to another graph. So we'll talk about this stability of domains under deformations in a few minutes. Okay, so a better idea is to apply a spectral filter to the graph Laplacian. And when I say that I apply a function to an operator or a matrix, I mean it in the operator sense that I need to apply to the eigenvalues of the matrix. So if I apply this spectral transfer function p hat to the matrix delta, to the Laplacian, then I can write, and in this case, I assume that it is a polynomial with learnable coefficients alpha. I can write it in this way, right? And just amounts to, apologize, some disturbance here. Sorry, guys, I'm getting some noise. Yeah, sorry for that. There was some noise on my side. So basically, what we get here is quite an interesting situation, because to compute this function, I actually don't need to do any explicit eigendecomposition. I can just take the powers of the Laplacian and combine them. What is also interesting that the structure of the Laplacian is exactly as the structure of the adjacency matrix of the graph, right? So the complexity of multiplying by such matrix will be equal to the number of, or order of magnitude of the number of edges in the graph. And in many graphs, such as social networks, this is roughly equal to the number of nodes in the graph. So it scales linearly, not quadratically. We can also show that it's stable under deformations. So if I slightly change the graph, the result will not change dramatically. And this is a nice property. There are multiple results that show it. And what we also see here, that this spectral filter with graph Fourier transform actually boils down to simple local averaging. So this is exactly the convolutional flavor of graph neural networks that I showed before. And many references in graph machine learning make this distinction between spectral and spatial filters, but actually there are two sides of the same coin. And let me show you why. So the way that we can think of this, applying this spectral transfer function to the Laplacian, is essentially a filter, right? So I evaluated the eigenvalues of the Laplacian, right? And we can think of it as the Fourier transform of some filter, let's call psi hat, that I apply to the Fourier transform of X. And here I allow myself to write it in a more general way. So the Fourier transform is a projection or an inner product of some signal with basis functions phi. And the inverse Fourier transform amounts to multiplying the basis functions by the Fourier coefficients and summing everything up, right? And this can be done on any domain. It can be graph, it can be manifold, it can be anything, right? So this is exactly our definition of spectral convolution, the pointwise product in the Fourier domain. Okay. Now I can also, so here I write the inner product as an integral over some domain omega, right? If it's discrete, then it will be a sum, and I exchange it with the summation. So what I get is an integral over xu multiplied by some kernel. Let's call it psi of u and v. So this is position-dependent kernel, right? So for every u, it will look differently, right? And there's a sanity check. If I assume a Euclidean domain, then phi's are just complex exponentials, and due to associativity of exponentials, I get here a function that doesn't depend on u and v. It depends on the difference between u and minus v, right? I can do this difference on the grid. So this is standard convolution, right? So it boils down on a grid or in the Euclidean domain to the standard convolution. So question regarding spectral filters in analogy to the filters in signal processing, how the spectral bandwidth of eigenvalues are universally defined across different graphs? So this is actually a deep question. So on domains such as two-dimensional grids, you have natural multi-dimensional structure of frequencies, right? Because you can write a two-dimensional grid as a tensor product of one-dimensional grids. On a graph, you have one-dimensional frequency. You just sort the eigenvalues in increasing order. And so in this case, the filter will be applied to eigenvalues of that respective graph. So, for example, you can say that my filter is a low-pass filter, right? So in this case, I have a filter that passes the low frequency and the mid frequency, right? So this is how it looks like. So you can show that it generalizes nicely and is stable under graph perturbations. And there have been multiple works, as I said, so it has been used in computer graphics as early as in the 90s by Gabriel Taubin in the domain of graph signal processing about a decade ago by José Moura and Pierre van der Geijns and then others. And then, of course, you can choose different filters. So polynomial filters were used by Michael de Ferrar in the ChebNet architecture and in graph convolutional networks, GCN, the work of Welling and Kipf. We also used a different version with rational filters, what we call KaiLiNet, and there are many other flavors and versions of these spectral GNNs, but I hope that you can see that these are instances of exactly the same blueprint. Okay, if there are no questions, let's talk about what is called homogeneous spaces, or where our group construction will be more interesting and more prominent. And as we've seen in our discussion of convolution, so the spatial interpretation of convolution, you can think of it as a kind of sliding window or pattern matching, right? So in an image, I just take some mask that is learnable and I slide it over the image, right? So let me formalize it slightly. What I want to do is I need three things, right? So I need the filter that I denote here by psi. I need a way to shift it around. So this is given by the shift operator that by t_u, right? U will be the vector by which I shift. And then I need an inner product that will match the filter to the image, okay, or my signal. So if I compute this inner product for every position of the shift, I will get the convolution, right? So the convolution has the same structure. The output of the convolution has the same structure as the input, right? Now, this is a very particular setting, right? Because this is actually a situation where I can identify my group with the domain itself, right? So even though the group is completely different from the domain, it's completely different animal. In this case, I can say that a shift, right? I can represent it as a point to which I shift. So there is a one-to-one correspondence between the domain, the grid or the plane, and the structure of the translation group. But this is not generally the case, right? In general, I might have some general group, right? So it acts on signals through its representation rho. And now I need to compute this inner product for every element of the group, for every G, right? So the output structure will have the structure of the group. The input structure will be the structure of the domain, right? I hope that this distinction is clear. And it's not necessary that these two structures coincide. So let me give you an example. So here is how to do convolution on the sphere according to this blueprint. So in this case, the sphere is a two-dimensional manifold, right? So it's what we call three-dimensional sphere. So we can represent it as unit vectors in R3, right? Let's call them U. Now the group here will be the group of rotations, what is called special orthogonal group, SO3, right? So these are rotations that preserve orientations. I can represent them by matrix R that acts on these three-dimensional vectors, and this matrix is orthogonal and has determinant 1, right? So these are rotations, and I rule out reflections that would have a determinant -1, okay? So this is how the convolution will look like. For every rotation, I compute the integral of the image, right, or the signal on the sphere with a transformed filter. And the problem is that the output is a signal on SO3, and SO3 is a three-dimensional manifold. It's a Lie group, and you see why easily why we have three dimensions here, because we have 3 degrees of freedom. On the sphere, I can rotate this way, I can rotate this way, and I can rotate this way, as I show in this picture with the smiley. So the output actually will live on SO3. So if I want to apply another layer of convolution, I now need to integrate on SO3 rather than on S2, right? And this is something that by chance, right, or by lucky coincidence, we had this identical input and output structure in convolutions on the grids or on the plane, that we can apply a sequence of convolutional layers, and the convolutions look the same. Here they don't. Right, so the first convolution is on the sphere, but the second is on SO3. That has to be done differently. Okay. So even this, so here we already moved beyond grids, right? So we are moving from Euclidean domains to non-Euclidean domains. A sphere is an example of what is called a manifold, right? But it's still quite special. And the special thing here is that on the sphere, if you look at it, there is complete democracy. Every point is exactly the same as other. What I mean by this is that I can take any point and transform it into another point by the rotation group, right? So there exists an element of the group such that GU equals V. So we call in geometry such spaces are called homogeneous, and their key feature is global symmetry structure. Now, this is not the case for general manifolds. And this requires an extra leap of mathematical machinery, and allow me not to go into all the details. But maybe first, you may wonder why at all we are interested in manifolds, right? So these are quite exotic constructions that are used in pure mathematics. Why at all in machine learning you should be caring about these things? So I would like to give the motivation from the domain of computer vision and graphics. So in vision and graphics, we often need to deal with 3D objects. So these are volumes, right, of in our physical world, right? So I don't know, I take this cup, right? So this is a 3-dimensional volume. But if I look at it, for example, if I sense it with a 3D sensor, I don't see what's inside, right? So I see only its boundary surface. So the boundary surface, mathematically speaking, is a 2-dimensional manifold, right? So if I were to represent this object as a volume, right, as an array of voxels, I will waste a lot of representation power, right, a lot of memory to represent something that I don't care, right, the inside of this bunny, for example. So a much more natural representation in this case will be a surface that can be discretized as a mesh. Now, another thing, when in computer graphics, for example, or in vision, we need to deal with deformable shapes like the human body, then it is very natural and very easy to describe different deformations as deformations of the manifold rather than some manipulations with the volume. Now, another application comes from the field of structural biology, and I hope we have time to talk about it, about representation of proteins. And proteins are complex biological molecules that fold into very intricate structures like is shown here. So what you see here is a plastic model of a protein. So the colored ribbon diagram shows the backbone of the protein, but the transparent plastic shows the molecular surface. So this is how another molecule sees the protein. And if I am another molecule, a drug, I don't see what happens inside. I see only what happens on the outside. So a drug will look for some pocket-like region on the protein to attach to it chemically, to bind, as chemists say. So this way, if I consider it as a surface, I can abstract out irrelevant internal structures that are not interesting for interactions. And I can also allow the protein to change conformation, to slightly deform. Okay. Now, we've already seen the manifold, right? When we talked about the sphere, it is a manifold, but it is a very special space where we had this global symmetry structure, where we had it was a homogeneous space. So I could move from a point to another point by means of a group element. So in a general manifold, I don't have this global symmetry group. I don't have a group that allows me to move from one point to another, right? So there are multiple paths that take me from one point to another. So there is no canonical path, right? Or at least not immediate. I cannot describe it as a group. And therefore, the results of moving things around will depend on which way I go, right? So again, this mental picture of a convolution, think of it as take a filter, right? That is some local kernel, and move it around your domain. And in the plane, it doesn't matter how you go. Whether I go the red way or the green way, I will get to the same result, right? The filter will not change orientation. We call this parallel transport. On and non-Euclidean domain, the result will differ. So even on the sphere, if I move along the green path or the red path, I will change the orientation of my filter. This happens because of the curvature, because what is called a connection that rotates these local vectors. So here's another example. This is a non-orientable manifold where the field of normals is discontinuous, what is called the Möbius surface. And you can see here we have reflection ambiguity. I can go this way, and then then I don't change the orientation of the filter. But if I move along the green path, I will change a right-handed system of coordinates to a left-handed system of coordinates. So you can already see that this kind of convolution is non-trivial on manifolds, and there are multiple ways to deal with it. So you can fix the path. So you can say, for example, let's move filters along geodesics, and locally you can do it. You can say, let's fix the gauge, right? So this local system of coordinates. So if I were to prescribe some canonical local frames, right, we'll define it in a second more rigorously. For example, on the sphere, we have a canonical parameterization, then I get rid of this problem. We can do spectral filter, and in this case, we completely ignore orientation, so our filters are isotropic. And this is what the representation does, because, as I mentioned, the frequency is one-dimensional, so it is oblivious to directions. So you don't have a natural notion of direction on a graph. And finally, we can construct, in the spirit of this geometric deep learning blueprint, filters that will be equivariant to the local transformation of these coordinates. Okay, so this will be what I will describe next. Now, maybe not everyone here knows what a manifold is, and allow me to skip important details because we can spend an entire course on manifolds in differential geometry. So what you need to know about manifolds is that these are topological objects. So topology roughly is a kind of flexible geometry where you have the notion of neighborhood but not distance, right? And there is this famous joke about a topologist's breakfast that you can take a cup, you can drink your coffee, right? And then you can deform the cup into a donut and eat it. Basically, these two objects are topologically equivalent to a torus. So a manifold is a locally Euclidean space, meaning that you can take a point and a small neighborhood around it, and you can map it bijectively to a Euclidean space. Okay, and we say that the manifold is smooth if different ways of mapping, right, what is called transition functions, are smooth. Okay, now locally you can model a manifold as a Euclidean space. This is called the tangent space. The dimension of this space is the dimension of the manifold. So in this case, we're talking about surface or a two-dimensional manifold. So locally, it is homeomorphic to a plane, right? And we can call it the tangent plane. Okay, so as I said, a manifold on its own, a naked manifold, has no structure. So a standard way in geometry to introduce this structure is in the form of what is called the Riemannian metric, which is simply a local inner product on the tangent space. And it allows us to locally measure length, angle or direction, and areas, right, or volumes. So it induces a volume form. And any property that can be expressed in terms of the metric is called the intrinsic, and any deformation that doesn't change the metric is called isometry. In Greek, it means equal metric, right, or metric preserving deformation. And you can see that we can use this construction to define something that looks like similarly to convolution on the manifold. Basically, we have a filter that is applied locally in the tangent space, right? And then we have some construction that allow me to skip the details that is called the exponential map that goes from the tangent plane to the manifold. So it's a unit step along the geodesic if you want to know how it is defined. So basically, I can define the filter in the tangent plane and then fetch the function from the manifold using exponential map and multiply it by the filter. Okay. Now, what is written here, you can write it on paper. You cannot implement it on a computer because what is written here are abstract geometric vectors, right? And you need to understand this is probably one of the big crimes against humanity that are committed, especially at school, when you're told that the vector, you can think of it as an arrow or you can think of it as an array of coordinates. So vectors are neither arrows nor arrays of coordinates. Vectors are just defined by by a set of rules that allow you to add two vectors and multiply them by scalars. So if you want to think of them as directions or arrows, you need to define an extra structure that is called an inner product, right? That makes it into a Hilbert space. Or if you need to define a norm that allows you to measure the length of a vector. If you want to define a vector as an array of coordinates, you need to provide a basis. You need to provide some reference frame with respect to which you decompose your vector. So we have nothing to do with these vectors. We need to assign some reference frame, right? What is important in this construction, though, that it is defined intrinsically. So if the exponential map is intrinsic, as a result, it's invariant to the isometric deformations of the manifold. We'll talk about this notion of domain deformation in a few minutes. Okay, so I need to choose some local frame, right? And this is what physicists call the gauge. So exactly the same gauge that I mentioned in the beginning in physics from the gauge theory. And the gauge is just a fancy name for the choice of a local system of coordinates on the manifold, right, on the tangent spaces, which changes smoothly. If I move a little bit from a point, I will not see an abrupt change in this frame. Is the exponential map related to the matrix exponent? Yes, it is related. Yeah. So matrices also form a special kind of manifolds, and it is related. Yeah, but allow me not to go into these details. So you can see that on a manifold, the choice of the gauge is arbitrary. So it is defined up to some transformation that is modeled as a group. This is called the structure group, right? And this is structure group that is associated with this manifold, or more correct, what is called the tangent bundle. So this collection or disjoint union of the tangent spaces. And we can choose it in many different ways. And it depends really on the amount of structure that we assume. So this is again a recurrent topic in geometric deep learning, that you have some control of what kind of assumptions you make on your domain or on your data. So, and as I said, on the naked manifold, you don't have any geometric structure. So here, the change of this gauge can be anything, right? It just must be regular. So it must be an invertible matrix. So we call this the general linear group. If the manifold has orientation, it must be an invertible matrix with positive determinant. So I cannot change the handedness of my frame. I cannot go from left-handed frame to right-handed frame, right? So I cannot have reflections. If I have manifold with volume form that can be defined separately from the metric structure, then I have matrices with determinant 1, right? So I have I can preserve directions. Sorry, I can preserve volume, right? Determinant 1. Determinant tells you how volume shrinks or grows. If I have manifold with metric, I can preserve angles, right? So I'm talking about orthogonal matrices that rotate or reflect. And if I have manifold with metric and orientation, then I have orthogonal matrices with determinant equal to 1, right? What is called the special orthogonal group that we've seen before. So it's rotations without reflections. And finally, I can have a situation where I have a manifold on which I can define a frame field. In this case, the group is trivial, so there is no ambiguity, right? And to make it less abstract, so here is a two-dimensional surface. Here I have a manifold with Riemannian metric, right? And it's orientable, so the ambiguity is two-dimensional rotation. I don't have a canonical way of preferring certain orientation. If I have the Möbius surface, so it's a plane. So in plane, we have no ambiguity, right? But because it is twisted, we have here reflection ambiguity, right? I can flip my coordinates from left to right-handed. And if I have the sphere, for example, right? Let's assume that I remove the two poles. I have a canonical gauge, right? I can the typical frame that we assume on the Earth is azimuth and elevation, right? The parallels and the meridians on the globe. So in this case, there is no ambiguity whatsoever, right? With the exception of these 2 points. So because we are dealing with surfaces, right, with Riemannian manifolds, actually the metric is induced from the embedding of the manifold in some space. We are interested primarily in these 2 situations. So it is reasonable to assume that we have only special orthogonal group, so only rotation ambiguity in the tangent space. And actually, it is interesting that even though in principle you cannot define a canonical gauge. And actually, not only ambiguity, it is in principle impossible on a sphere-like object to have a smooth vector field. So this is what is called the hairy-ball theorem, or more formally the Poincare-Hopf index theorem. So it tells you that if you have a vector field on the sphere, it must vanish at least at one point, right? And why it's called the hairy ball. So imagine that you have a sphere with hairs, right? Like my hair on the head. And if I try to comb it, there will always be a point of a vortex. If you think of winds on Earth represented as a tangent vector field, then the Hopf-Poincare theorem guarantees that will always be a point on Earth where there is no wind, which is an interesting thing. This is also one of the reasons why in confinement chambers that are used in plasma physics, you cannot have a spherical chamber. It must be a toroidal chamber. And that's exactly the reason, because the magnetic field must be smooth, and on the sphere you cannot have it, right? So that's why the plasma runs in a torus. You can comb a torus, you cannot comb a sphere. Okay, so that was a little bit of a digression, but bottom line is that maybe with the exception of a few singularities, there are actually practical methods to compute stable gauges on manifolds. And we had such a paper at last year's CVPR called G-frames. So this is where practice slightly diverges from theory, and some of the first architectures of intrinsic convolutional networks on meshes actually assumed such canonical fields. But of course, it's not very nice. So it is actually possible, same way as we did, for example, with standard convolutions where we have equivariant operations, it is possible to define equivariant convolution-like operations on manifolds. So that was a nice work of Taco Cohen and Max Welling. So in this case, if I change the gauge, if I rotate it locally, then the filter will transform in the same way, right? So if you look at manifolds, we have two types of invariance. So we have this local arbitrarity in the choice of the gauge or the reference frame, and we also have the global deformation, right? And let me say a few words about this global deformation. So if you remember, we had basically our model that we discussed so far was about signal deformation. And what I mean by this, that we had a signal that lives on some domain, right? X lives on omega, let's say grid. And we did something to this signal, right? We applied to it a representation of some group of the domain, rho of G, and something happened to this signal, right? Let's say it's shifted or maybe deformed in some way. And we guarantee that if we construct the function to be invariant to this group, then as long as I act with a group on this signal, the output of the function will be the same. Okay, so here we have a different situation. Here we have a different domain. So I'm not deforming the signal, I'm deforming the domain on which the signal lies, right? So imagine that you have a situation like this, where we have some surface, and I draw some image in it, right? This checkerboard. So I'm deforming the domain on which the image is drawn. And what I can guarantee by making my function intrinsic is that it will be invariant to these isometric deformations, right? And then if you remember, we had a generalization of this result. We could talk about geometric stability or approximate invariance to deformations. So here we could say that if I have a general operation like our warping, then the difference between the output of the function on the original signal and the warp signal will be bounded from above by something that measures how far this general warping is from being a group, right? So in case of domain deformation, we can also extend it and say how far is omega wave the deformed domain from being an isometry of the original domain. And you can imagine this situation where we not only fold or deform this piece of paper, but we can also allow it to stretch, right? And in this case, of course, the output of the filter will not be exactly the same, but it will be close enough, right? So there will be some continuity, there will be some stability. And where it's important in applications in graphics and vision, where, for example, we want to find correspondence between deformable shapes. So this is a common step in building three-dimensional avatars. So you can see here that, for example, these two poles are approximate isometries, right? So our body is a good example of near isometric deformations, but for example, these two shapes are not, right? So these are different people. So you can think of it as approximate isometry, but there are also some stretching, right? So one has maybe a fatter body. So there is some stretching that goes on, right? And what we can guarantee that the output of such convolution will not be too far from the original one. Okay. Any questions on this before we talk about applications, and if I have time, about some open directions? So the question is, the domain deformation, does it act on the labels while leaving the data alone? So no, so it acts, so these are two components of the same thing. So the input to your machine learning system is both the domain and the data. So maybe let's take an example of graphs. So on the graph, you can change the signal, right? Or you can change the graph itself. So you want to be stable to both operations. So I want, for example, to, I don't know, remove one atom from the molecule, and I don't want something abruptly different, right? So let's talk about applications in computer vision and graphics. And again, when it comes to dealing with three-dimensional objects, there is plenty of different ways of representing them. And it really depends on the application and what you want. So it's not exactly a universal recipe. So for example, in medical imaging, actually the acquisition of the data, the medical imaging modality itself makes it natural to work with volumetric representations. And there are two additional considerations. So in medical imaging, typically the objects are aligned. So for example, when you insert the patient into a CT scanner, the patient is not lying on the side one time or rotating the head, so there is always a certain pose. So at least roughly the objects are aligned. Second, you're interested in what happens inside. You actually usually don't care what happens outside, right? So there are some values in these voxels inside the body. If, on the other hand, you're scanning an object with a 3D sensor, you don't see what's inside, you only care what happens outside. So in this case, for example, it will be convenient to represent the object as a mesh or maybe as a point cloud. So point clouds are actually very common in self-driving applications because this is how the data comes out of the LiDAR sensors that are used in this field. And there have been multiple works. Recently, they used geometric deep learning architectures to analyze these point clouds and to reason about, for example, moving cars in a complex scene to prevent and avoid collisions. So in computer graphics, well, this is probably one of the prototypical applications, marking-less motion capture. So here the actor is captured in real time with a 3D sensor, and then the deformations of the face are transferred to this Shrek-like creature. So you have two problems here. One is the problem of analysis. So you want to find correspondence between the noisy scan input and the canonical structure of the face. And then you have synthesis where you deform this canonical face into this Shrek face that repeats the expressions. And we used geometric deep learning architectures for these kind of applications, building 3D avatars. You can also have hybrid architectures where the input is a two-dimensional CNN that inputs an image or a video, and the output is a geometric mesh CNN that reconstructs the shape and the pose of a three-dimensional hand, right? So reconstructs a mesh. So this was the work of my PhD student, Dominique Coulon, and we collaborated with a British startup called Real AI to create this real-time demo of 3D avatars of people with detailed faces and hands. And this was a startup of a friend of mine, Iasos Kokinos, that was acquired by Snap last year. So we can already find this technology in Snap products. And well, I have minimal credit here besides being one of the investors and convincing Iasos to leave his industrial job to do this startup. So another interesting field of applications is physics, in particular particle physics. And here I'm quoting Kyle Cranmer, professor of physics at NYU and one of the discoverers of the Higgs boson in the Large Hadron Collider. And he writes that it was amazing to see how GraphML has become very popular in the field of physics. And again, in particle physics, this is one of the hot topics. So this is one of the detectors in the LHC. And colliders are probably one of the most complicated and expensive machines ever built by humans that accelerate particles to almost the speed of light and then bang them together, producing these jets or showers of particles, where they then search for different evidence of interesting interactions, or maybe new particles that never existed before or never observed experimentally. And actually LHC was built to find experimentally the Higgs boson, which it achieved successfully. And you can represent these showers as graphs. And graph neural networks are now prominently used in this field for a variety of applications, such as reconstruction of particle jets. For example, you want to see where different points register by these detectors to what event or to which interaction they belong, but also for classification of different events. In LHC, most of the events are not interesting, so they actually use hardware to filter out most of the events that don't contain signs of interesting physics that you can tune for a particular experiment, because otherwise you would need to store a huge amount of data that you simply technically cannot do. The collider produces petabytes of data every second of its operation. There are millions of collisions that are happening every second, and the detector produces a lot of output. So I myself, we collaborated with another particle physics experiment that is called IceCube. And you can see it here. This is Neutrino Observatory on the South Pole. And this is literally the tip of the iceberg, because the detector itself is not seen. It's a cubic kilometer detector under the ice. And you need this volume because neutrinos are almost never interact. So when they interact with matter, they produce what is called Cherenkov radiation that is picked up by these photomultipliers in the ice. And they produce this kind of signature. So here, I think this is what is called four-dimensional momentum of this particle that you can measure. And the idea of event classification here is you want to detect neutrinos from astrophysical sources and separate them from background. So one of the problems in these experiments is that you have a lot of noise, and you have maybe very few interactions that might come from, I don't know, some black hole in a galaxy far, far away that collides with a star and produces a shower of neutrinos. So you want to register these kind of events and then observe the same object with traditional astronomy, and this now with also the possibility to record gravitational waves gives what is called multi-messenger astronomy. So it's completely uncharted territory. Exciting times to be an astrophysicist. So another prominent application of graph neural networks in geometric deep learning is in social networks. So probably the first application was for recommender systems in Pinterest. So that was the work from the group of Yuri Leskowitz on GraphSage and PinSage. And the typical way that you do it, you create an embedding of the nodes of the graph, and you try to associate the proximity or distance of the latent representations of the nodes to the probability of an edge existing in this graph. So it's a kind of link or edge prediction. And of course, there are many nuances and flavors to this problem. So multiple companies that need to work with recommendation systems have implemented certain forms of graph neural networks or GraphML in their platforms. So what I show here is a paper called AliGraph from Alibaba that now uses graph neural networks in their commercial products. So I myself, with my students, we founded a company called Fabula AI, where we used graph neural networks to look at the spread of news on the social network, and by the propagation patterns to try to detect misinformation or what is called fake news. And this company was acquired by Twitter 2 years ago. So now I had a group that does research on GraphML. And you can imagine that graphs of different types, such as the follow graph or the engagement graph, or maybe other graphs that are not publicly exposed by Twitter, are some of the key data assets for the company, and they can be useful and meaningful in a lot of use cases and scenarios, from detecting misinformation to recommender systems and so on. So let's talk about structural biology. So I always made these connections to chemistry and biological problems, and I would like to start talking about proteins. So again, probably most of the crowd here is computer scientists, so let me give you a 2-minute crash course on biology, what you need to know. So in biology, there is what is called the central dogma, which tells you roughly that the DNA encodes proteins. The way that it is done, as you know, DNA is a very long sequence of nucleotides that are represented by 4 letters, A, T, G, and C. And there are about 2 billion of such letters in our DNA. So there is a counterpart strain that then is folded into or rolled into double helix structure. That is the famous structure of the DNA molecule. And every triplet of such nucleotides encodes 1 amino acid, the basic building block of a protein. So there are many more amino acids, but there are 20 what is called proteinogenic amino acids. So all natural proteins are built out of these 20 components. And you can see here the table that shows the encoding. So this code is redundant. There are 64 different combinations. And you can see that there are some combinations that encode some amino acids. Why it is exactly like this, nobody knows, as far as I know. So this is really one of the big mysteries of nature or evolution. So what happens next? Basically, there is some chemical machinery inside the cell that reads out the DNA. So technically speaking, it's first transcribed into an RNA where one of the nucleotides is replaced by another. And then it is translated to amino acids. So there's also special markers that tell you when to start, when to stop. Bottom line, it's a long sequence of amino acids by a biopolymer that then, under the influence of electrostatic forces, folds into complicated 3-dimensional structures, what is called secondary and tertiary structures. And a good analogy is this snake toy, which is 1-dimensional, but it is flexible and you can fold it more or less in anything you want, right? So it is this 3D structure that gives the protein its function, because it serves as a kind of domain on which, for example, chemical reactions happen. So it serves as a catalyst, what is called enzymes. There are some other molecules that might fit into this structure as a key fits into a lock, right? And again, this was the analogy that was used by Emil Fischer in the late 1800s, also Nobel laureate in chemistry, to describe how, in his opinion, enzymes work. So that's exactly how it works. And one of the classical problems in bioinformatics is what is called protein folding. So you start with a sequence of amino acids, right? The primary structure of the protein, and you try to predict how it would fold in the 3-dimensional structure. And it was conjectured by Anfinsen, chemistry Nobel laureate in the 70s, that the folding is completely determined by the sequence of amino acids in a certain environment, basically in the solvent, for example, if the protein is in water. And people have been working for 50 years trying to predict the 3D structure from the amino acid sequence. And there are crystallographic techniques. You can crystallize proteins and using X-ray crystallography to get their 3D structure. This is how traditionally the 3D structure is recovered. This is how, for example, the structure of insulin was first reconstructed. One of the first proteins ever whose structure was built. And there was a competition called CASP, where similar to ImageNet, where you're given some proteins for which the structure is withheld. You're only given the sequence. You're also given an evolutionary history, because organisms evolve, DNA code changes, and as a result there are some small changes in the protein. But because proteins need to maintain the same function, otherwise the organism will not live, the structure roughly is preserved, right? So you can use this information to help predict the folding. And there happened this ImageNet-like moment in the CASP competition in 2018 when a newcomer, an algorithm from DeepMind called AlphaFold, was able to beat by a significant margin previous existing approaches. And this year, AlphaFold 2 achieved even more significant accuracy. And actually, if you look at how the algorithm is structured, it uses this geometric deep learning principle. So it uses a graph neural network with attention, right, or they call it transformer, with equivariant message passing. Again, in the paper, they call it invariant point attention. So that's exactly somebody asked about molecules. So in molecules, you want your message passing on the graph to be equivalent to three-dimensional transformations. So you don't care, roughly speaking, how a molecule is positioned in the space. So you want, if I rotate my molecule, I want the output representation to be rotated in the same way. So that's exactly what is implemented there in AlphaFolds too. And why proteins are important? Because roughly speaking, proteins are everywhere. So these are molecules of life. We don't know any life form that is not based on protein. From take any system or any process in the body, it is likely that it will be powered by proteins somewhere, whether it's a defense against pathogens, antibodies, or proteins. When you're breathing, you are doing it because the molecule of hemoglobin binds oxygen and brings it to your cells. This is a special kind of protein. Your cells are able to function because they can transport stuff across the membrane using what is called the calcium pump, which is also a complex of proteins. I already mentioned enzymes that make possible catalytic chemical reactions. Even our skin is flexible because of a special protein that is called collagen that we lose, and that's why we get wrinkles when we get old with age. So being so ubiquitous, proteins are an obvious target for drugs. So if, roughly speaking, a drug tries to attach itself to a protein and enable or disable some chemical reaction, right? And typically drugs are discovered or developed to bind these pocket-like structures. So what is shown here, well, it's not exactly a drug, it's a drug-like molecule. So it's one of the xanthines, so the same chemical class of caffeine that is found in coffee and tea. So when I take a cup of tea, in this case, what I have here, and I drink it, and I do it a zillion of times in my talk, so apologies for that, for sounding redundant. This molecule gets into my brain, binds to a protein that is called adenosine that acts as a receptor and makes me feel awake and feel happy and whatever. Right, so this is how drugs are designed. So you can either discover a drug or design it to bind to such pocket-like structures. Now, in recent years, the pharma industry is interested in what is called protein-to-protein interactions, or PPIs. And they're interested in drugs that disrupt these interactions. So you want to prevent two proteins from binding together. And the problem with these kind of drug targets is that they don't have these pocket-like interfaces. Most of the PPI interfaces are flat. So the idea is that you can try to build a new drug that is called a biological drug that is a protein itself, and it can attach to another protein. And one of the prominent applications where this is used is in cancer immunotherapy that was awarded the Nobel Prize in Medicine in 2018, what is called checkpoint immunotherapy. And what happens is that in our immune system, we have a special signaling mechanism that allows the T cells, right, the cells that are responsible for killing pathogens, to indicate that this is a healthy tissue, so don't kill me. And some cancers express this protein. It's called PD-1, PD-L1 complex, program death complex, and they inhibit this way the normal function of the T cells. And as a result, the tumor grows unaffected, and then we have a problem. So immunotherapy is a way, and sorry for maybe oversimplifying for people working in this domain, roughly speaking, it's a way of giving back control to the immune system. So you would like to block one of these proteins, either PD-1 or PD-L1, by attaching something to it. In this way, this mechanism is disabled, and then the T cells happily destroy the cancer tumor tissue, and you get rid of it, and you live happily ever after. So to do it, you need to build a protein that has certain properties, right? So in a sense, it's an inverse folding problem. So it's protein design. You know what structure you want to get, right? And you want to come up with an amino acid that will have this three-dimensional conformation that will fold into this structure. And somehow, at least naively, you can think that, okay, I have a sequence, right? The primary structure, it folds into something, and then some three-dimensional structure. And we know that, at least hypothetically, it is completely determined by the sequence, and then the structure endows the protein with its function. So, for example, two proteins stick together like pieces of 3D puzzle. Now, of course, this is far from being true, and there are many examples where it doesn't work. So you might have proteins with very similar sequence, but very different structure. So some cases you can just change one amino acid and everything breaks, or you can have proteins with very different sequences but very similar structures. And I think evolutionary biologists call it convergent evolution. And maybe I'm saying something silly, but you might have different organisms that learned the same function, right? Or the same protein that came from completely different evolutionary history, right? So completely different sequences, completely different genetic code, but same stuff, same structure. And finally, you can have proteins that bind to something, but they have a very different structure and very different sequence, right? Again, you might think of a puzzle where there are multiple pieces that can fit well, but they look differently. So with my collaborators at the PFL, we developed a geometric deep learning architecture that we call Massif that allows to predict the binding properties of proteins and, for example, to predict the regions where that are likely to bind other molecules by doing these surface-based convolutions. And this is an important ingredient in what is called de novo protein design, where we design proteins from scratch. And again, maybe somehow the popular press makes it sound that deep-bind AlphaFold has solved everything that you have to do with proteins, but it is far from truth, because they rely on evolutionary history. And in de novo design, for example, you don't have evolutionary history. So you're building a protein that is first ever, never existed in nature, right? So you are the first one to do this protein. So no evolutionary history. You cannot rely on anything that is similar to it. So you're really building protein from scratch. And you can use these geometric deep learning methods for this purpose. And here you can see 3 designs that were actually tested in the lab, for which we have crystal structure obtained, and they bind to this oncological PD-L1 target, and well, maybe sometimes in the future can be used as drugs against cancer. So talking about chemistry and drug design, well, I think you know that it takes a lot of time and a big effort and a lot of money to develop new drugs, about $1 billion and about a decade to bring a new drug to the market. And the reason is that there are multiple stages of different very rigorous tests that drugs are subjected to. So you want to make sure that the drug can be delivered, it's not toxic, it really binds to the target, it doesn't have side effects, and so on and so forth. And it's an iterative process. And as you go deeper and deeper, it's more and more expensive. And what can be done with machine learning and computational methods is to try to virtually screen the drugs for promising candidates that then can be modeled and tested in the lab, because the number of possible molecules that in principle can be synthesized is humongous, something like 10 to the 60. On the other hand, the number of molecules that you can test in the lab is probably in the range of thousands or maybe tens of thousands. Okay, and graph neural networks actually have been developed for this purpose, right? Remember this slide where the chemical analogy of graph neural networks, right, or similar algorithms for predicting properties of molecules by means of message passing that have been used in chemistry for decades. And nowadays, with modern data sets and modern algorithms, it is possible to incorporate these methods into real drug discovery pipelines. So this is a paper from the group of Jim Collins at MIT, where they used graph neural networks in a pipeline to predict antibiotic properties of drugs, and in particular, they found that an anti-diabetic drug candidate called halicin has very strong antibiotic properties. So it's actually, as a side remark, I come from Imperial College, where the first antibiotics were ever discovered and created by Sir Alexander Fleming, and it gave us about 100 years of huge success in medicine. So I think literally it saved billions of lives. And we are unfortunately now running out of this power. And it's not a question of if, it's a question of when that we'll have an antibiotic resistant bacterium that will become highly contagious. And if you want to imagine how it will look like, think of the coronavirus pandemic. Imagine that it's caused by a bacterium that against which we don't have any cure. So we need new kinds of antibiotics, and the sooner the better. So still talking about drugs, another interesting direction in developing cheaper and faster therapies is what is called drug repositioning, where you take existing drugs, instead of designing a new molecule and spending $1 billion and 10 years, you take a drug that already was successfully approved, and you try to use it against another disease, possibly in combination with other drugs, because some combinations provide nonlinear effects. Sometimes these effects are good, sometimes these effects are bad. So you want to understand what are the possible synergistic or antagonistic or side effects of these combinations. It's called combinatorial therapy or polypharmacy. And Marinka Zitnik, a couple of years ago, used graph neural networks to predict side effects of these combinatorial therapies. And here they used actually 3 graphs. One is the PPI graph, the protein-to-protein interaction. So proteins here are the drug targets, and the graph tells us how they are related to each other. Then the drug-to-protein interaction graph that roughly describes how drugs act on our body, right? To which proteins they bind, and then they try to predict edges in the drug-to-drug interaction graph. And with my collaborators at Imperial College and with working with the Vodafone Foundation, we tried to take these ideas of graph-based drug repositioning approaches to the domain of nutrition. And you may know that many foods coming from the plant kingdom contain ingredients that are drug-like. They, for example, come from the same chemical classes as anti-cancer drugs. I should say that a lot of the drugs that we now use actually have their plant origin, and this is sometimes reflected in their name. Probably one famous example is aspirin, for which the chemical name is acetyl salicylic acid. That the name comes from salice, the Latin name of the willow tree. And from ancient times, people were brewing the bark of this tree to get an analgesic effect. Another example is for anti-cancer drug is camptothecin, which is a substance that is contained also in a tree that grows in China. And the 4 synthetic analogs of this compound are nowadays used as successful therapies, chemotherapies against cancer. So bottom line, what we eat, we actually have no idea what it is, right? So if we buy some piece of food at the supermarket, we'll see on the package the content of proteins, carbohydrates, fats, vitamins, minerals, but we will not see anything about the content of polyphenols, flavonoids, and so on and so forth. So it's really a dark matter of nutrition that is not tracked and not understood and unknown, right? So what we try to do is we try to model the effect of drugs or molecules in general by the way they interact with protein targets. Exactly like I showed before. So we have a PPI graph that, roughly speaking, very abstractly models our biology. And the effect of the drug is modeled as a signal on this graph, roughly which proteins it binds to. And actually, if you think of drugs as something very specific and very targeted, the number that I had from somewhere is that on average, a drug binds to about 50 proteins. So ideally, you want to bind only one, but there are many side effects that are undesirable. So this is what this graph-based representation allows you to do. Then we can apply some graph learning algorithms. So we can take a training set of drugs for which we know anti-cancer effect, right? So these are drugs that were approved by FDA against certain forms of cancer. And we can train a classifier that will tell whether this molecule looks like an anti-cancer drug or not. And then we can apply it to other molecules that are not necessarily drug molecules. These are drug-like molecules contained in foods. And we compiled a data set of about 250 molecules or 250 different food ingredients that contain these molecules. And some of them were prominently rich with such potential anti-cancer ingredients that we called hyperfoods, like tea, citruses, cabbage, celery, and sage. And of course, well, I'm strikingly oversimplifying this work. A lot of the effort went into actually understanding what kind of effects these molecules have in order to be able to convince people working in biomedical domain. So, for example, we're looking for effects such as anti-proliferation or anti-angiogenesis. So these are typical processes that are associated with the growth and spread of cancer cells. So we want to confirm that the substances that we identified by this graph-based learning method indeed does what it should do. Probably what is most interesting and coolest part of this project that food, of course, appeals to everyone, and we collaborated with the famous Italian chef Bruno Barbieri that used the ingredients that we identified to cook short recipes for Christmas. And if you wonder why he's in bed in this video, this is part of Vodafone citizen science campaign called Dream Lab. And this was a collaboration where the users of Vodafone contributed the idle power of their smartphones at night to allow us to make these computations in a kind of distributed platform. So I think I'm running out of time. So in the remaining probably 15 minutes, let me say a few words about the next steps or interesting directions, in my opinion, and open questions. And here actually I will follow a blog post that I wrote in the beginning of the year, where I interviewed some people that are prominent researchers in this field of geometric deep learning and graph machine learning. And one of them is Will Hamilton from Mila, who said that in 2020, that was recap of last year, we saw the field of GraphML come to terms with the fundamental limitations of the message passing paradigm. And here he refers to this equivalence that was shown between the Weisfeier-Lemon graph isomorphism test that I mentioned and the message passing architectures. So you can show examples of graphs that cannot be distinguished by the Weisfeier-Lemon architecture. So we need some stronger form of message passing. So we can still exchange information in the form of message passing, but maybe we need to do it with different structures. And there are multiple works that go in this direction. And here I'm showing a work that I did in collaboration with a group of Pietro Leo at Cambridge, where we extended message passing to simplicial and cell complexes. So if you think of meshes, these are prototypical examples. And another prototypical example are molecular graphs. Actually, chemists don't think of molecular graphs as nodes and edges. They think of them as structures. And they can, for example, think of rings as a separate object, of a higher dimensional object, a cell. And you can use message passing that takes this structure into account. And we can show that it's strictly more powerful than traditional message passing neural networks. And the results are very promising. It is also interesting that you can make explainable graph neural networks. And this is a cool paper from Karl Cranmer in collaboration with DeepMind. And what they did, they modeled physical systems of interacting particles as a graph neural network, where the edges are actually, the message passing functions are standard generic functions, shallow MLPs. And then they regressed symbolic equations from these functions and replaced them by symbolic equations. And what it gives you not only better generalization, as they show, but also interpretability. So you can actually derive the laws of motion from the data. And this is very cool because, well, I mentioned Kepler in the beginning of this talk. It took him his entire career, about 30 years, to analyze astronomical observations to come up with his law of motion, right? The elliptic orbits of planets. So now with this kind of technology, you can do it in a matter of a few seconds or maybe a few minutes, completely automatically. So it's interesting actually that there is this big argument between connectionists and symbolists, right? In artificial intelligence, let's say the placeholder, Yoshua Bengio and Gary Marcus. And this is probably a little bit halfway between. So it's maybe some effort of reckoning between the two, right? So this is very promising. So there is an entire field that is called algorithmic reasoning that also goes in this direction, and graph neural networks are a prominent candidate for it. And what I mean here is the following thing, that if you compare, so let's say that you have some graph structured data and you want to compute, for example, the shortest path between 2 points on the graph, right? So we know that you can use the Dijkstra algorithm, and we know that it will always work, right? So it produces predictable results. So I can give you any graph, right? So it generalizes perfectly across different data. And it is perfectly explainable. You know exactly what you get, right? On the other hand, it doesn't generalize across different tasks. So I cannot use Dijkstra to compute, for example, to partition the graph, right? On the other hand, neural networks, they are black boxes, so they're in most cases not very explainable. They somehow generalize to different data, but they often generalize very well across different tasks. again, I mentioned this example that a convolutional network trained on an image that could be used to reconstruct the event horizon of a black hole. Right, so algorithmic reasoning tries in a way to take the best of two of these worlds. Now, there are also interesting results, especially in the biological domain, trying to do causal inference. So you try to discover the graph of causal relations between different entities. And this is important, for example, when you want to understand the mechanism of disease. And also in medical domain, knowledge graphs are prominent, where these are heterogeneous graphs where nodes represent some entities and edges represent some semantic relations. And you can reason on these graphs. You can, for example, try to generate new edges or try to make some decisions based on these graphs. Now, another interesting thing, I already mentioned it, is, and here I'm quoting Thomas Kipf from Google. So he's one of the authors of the GCN, the Geodesic Convolution Networks. And he noticed this trend in GraphML community to separate the computational structure from the data structure, right? So remember what I showed in latent graph learning, and it has multiple manifestations in this field. One of them is graph rewiring. And this is a representative paper called Deagle, Diffusion Improves Graph Learning, from the group of Stefan Gunnemann, Thur, where they say that if you're given a graph, don't use this graph for message passing, embed it using personalized PageRank, and then compute nearest neighbor. So this way you get a different graph that somehow is similar to the original graph, but they show that doing message passing on this graph produces better results. And I personally, I have always been disturbed by this separation between the two worlds, right? So the continuous world where we have grids, where we, for example, we have a plane and we can discretize it on a grid, or we have a sphere and we can discretize it in different ways, and graphs that are somehow intrinsically discrete objects. And indeed, you can think of graphs, or at least some types of graphs, as a discretization of a continuous space. So there is an entire field that is called network geometry, for example, that tries to argue that, for example, social networks, or what is called scale-free graphs, can be obtained as nearest neighbor graphs in a space with hyperbolic geometry, right? So you can think of hyperbolic space as a kind of continuous tree. And it is interesting actually to interpret graph neural networks as a form of diffusion equations. So what graph neural network does is a diffusion of information. We can think of it as a kind of more complicated form of diffusion with a learnable diffusivity function that spreads information on the graph. And then the next step that we try to do, and that's a paper that we had at ICML this year, we call it GRAND, or graph neural diffusion, is to think of a graph neural network as a discretization of a continuous diffusion process. So we can discretize the time, which corresponds to the layers of the graph neural network, but we can also discretize the space. We can think of a different graph rewiring as just choosing a different discretization of our domain. And this is a very interesting and very promising research field that also has deep connections to differential geometry and some older works in the image processing domain, such as anisotropic diffusion. So talking about time, it is also interesting that in many cases, graphs also have a temporal component. So such as social networks, these are not static graphs, they evolve in time. So it is important in this case to be able to deal with graphs that are represented as some asynchronous stream of events that, for example, insert or delete nodes or edges. Then, of course, something that was important for computer vision was the availability of standardized benchmarks. So we already have something like this in the graph learning community, what is called OGB, Open Graph Benchmark. And it has brought some order in this wild zoo of different algorithms, maybe biasing it towards papers that try to squeeze 0.5% on the benchmark rather than thinking of more novel principles rather than trying to reach better performance. And probably one last noteworthy topic that I would like to mention is that several semiconductors companies are now looking into architectures that go beyond, let's say, GPU type SIMD, single instruction multiple data architectures. And there is this phenomenon in hardware, what is called the hardware lottery, when certain algorithms win not because they're ideally suited to solve a certain problem, but because they run well on existing hardware. So to some extent, this is what happened in deep learning. So convolutional neural network is not necessarily the best algorithm, right? So for example, it doesn't deal with rotations, but you can it runs very well on a GPU. So you can just throw more data on it and make it learn invariance from augmented data samples. Rather than incorporating this invariance to rotation into the architecture, as we've seen that is possible. So to wrap up, I hope to have convinced you today that we can use this notion of symmetry as a general principle that underpins deep learning. And it can be applied to different kinds of data, to different structures, whether it's grids, whether it's graphs, whether it's manifolds or other objects. And we can actually derive from these first principles some of the most popular architectures, whether it's CNNs, whether it's transformers or GNNs, and so on and so forth. And I hope that you will take this take-home message. I would like to finish with a quote from Helvetius, that the knowledge of certain principles compensates for the lack of knowledge of facts. And I think this is the main message that I would like to make today, that if you know these principles, hopefully they will survive more than a particular implementation of these principles in a particular architecture. So I will stop here and will be glad to answer any questions. Thank you very much.
Thank you, Professor Bronstein. Thank you very much for your excellent talk. And there is actually a 1 minute delay between us and the audience, so we need to wait for a while for them to type their question. So while we are waiting for the audience to type a question, probably I grab the chance to ask one. So my question is about graph rewiring. So in the end, almost the end of talk, you talk about graph rewiring. I'm kind of curious why graph rewiring really work, because if we do not consider the information from the edge, then graph neural network is very similar to just apply the self-attention, right? We have a group of points and we apply self-attention on it. If we do not use the edge information, it's hard to tell the difference between graph neural network and self-attention. Then why rewiring is considered as a better strategy on graph? Thank you.
Yeah, so it's a good question. So if you think of architecture such as transformers, so of course the computational complexity is very high, right? So you assume that anything can talk to anything. Rewiring, so you can understand rewiring as find a graph that is similar to the original one in some sense, right? That can be dependent on the input graph, dependent on the input data, and dependent on the task. But it's better in some sense, right? So it can be, for example, more computationally efficient. For example, I can try to sparsify the graph. This is what is done by sampling methods, but still I want somehow to preserve the structure of the original graph. For example, I can rewire the graph in a way that that reduces bottlenecks. So there is this phenomenon that in graphs, when you have problems where your task requires long distance interactions, and this is actually true in molecules, because in a molecule predicting some property might depend on the properties of atoms on two ends of the graph, right? And it might be something like 10 plus hops between these molecules that you need to pass the messages. So if your problem depends on long distance interactions, and if your graph has such a structure where the number of neighbors grows exponentially, like in social networks, then you run into what is called the oversquashing problem, where you have a lot of features that you need to squeeze into a single node, and you get this information bottleneck. So that's where graph rewiring can help.
Oh, thank you very much. Thank you for your insightful answer. And now we have several questions in the chat room.
Yeah, so let me start with quite multiple questions. So in
Yes.
applications of physics, chemistry, and so on, how to model more properties in addition to the geometry of an object, such as mass, charge, or even global environment properties, electric and gravitational field. Well, so there are multiple ways of doing it. And here, if we are talking particularly about graph neural networks, so probably the most general framework that has been described is, well, a little bit unhappy name, what is called graph networks. So that's the review paper of Peter Battaglia and others from DeepMind, where they assume, in addition to node and edge features, also have some global features, environment features. So you can also represent it as having a virtual node that contains this information that is connected to every other node in the graph, and they can get access to this to this information. So another question from Andrea, has been proven that it's better or more compute efficient or more accurate to use group equivariance CNN than just learn the rotation equivariance, for example, through heavy data augmentation. So the answer is yes. If you look at papers of, for example, Taco Coin, so they have specifically these examples. So here again, there might be some difference between what happens in theory and what happens in practice. In practice is that CNNs are so well optimized for GPUs that they're really the battle horse of in computer vision, that it's very difficult to move the community from these architectures. And in many cases, the data is so abundant and the compute is so cheap that you don't care. But of course, if you want maybe a more lightweight architecture, and maybe there are some other cases where maybe the structure of the group or the structure of the data is more elaborate, then you need to resort to these kind of geometric architectures. Which areas of mathematics should one learn to be effective in geometric deep learning, coming from a computer science background? Yeah, it's a good question. So I am also asked it often. So it really depends, because it's a very broad field. So, well, the obvious things would be geometry in some form, right? So either differential geometry, graph theory. Yeah, but I would suggest to start with our protobook, which somehow captures in almost self-contained way all the necessary background that is needed. Is there a relationship between the oversmoothing issue of graph neural networks and the fact that graph Laplacian is nilpotent? Okay, so it is. So first of all, graph neural networks are not necessarily based on the graph Laplacian. So by graph Laplacian being nilpotent, it means that it has a constant eigenvector, right? So there is a function that will be mapped to zero. So if I apply a Laplacian to a constant signal on the graph, right? Remember that Laplacian measures how different you are from your neighbors, and then of course you are not different from your neighbors if you have a constant signal. As a result, you will get a zero. So this doesn't explain the oversmoothing. So the oversmoothing is explained by the fact that typically what you do in the graph neural network is you apply some aggregation of your neighbors. Often it's linear aggregation just by the adjacency matrix, and this can be interpreted as a low-pass filter. So this is often the explanation. Another question. Could you repeat the difference between geodesic CNN and gauge equivariant CNN? Which method would you suggest to learn to solve computational fluid dynamic equations from data? Yeah, so I'm not sure about the second part of the question because I'm not an expert in CFD, but the difference between, so geodesic CNNs was the first architecture where we did learning on meshes. And there we dealt with this rotational invariance by using what is called rotational pooling. So this is a mechanism where you don't know how to orient your filter, so you rotate the filter and apply it to all the possible rotations of the patch, right, of the local patch, and then you compute the maximum. So it's not equivariant. You do this way some form of pooling to get rid of this ambiguity. In gauge equivariant CNN, you would apply a filter that changes in the same way as if you under the change of the gauge. So if I rotate my gauge, the filter will rotate in the same way. So that's the difference. So it's a more general mechanism that preserves more information. Is it safe to assume that any data manifold topology can be mapped to a hypersphere surface of the same dimension? So obviously the answer is no. I think this is usually not the case. Yeah, the same topology. So there are these results. Okay, so maybe I take it back. So for two-dimensional surfaces, you can do it. There is what is called the uniformization theorem. You can map any sphere-like manifold into a sphere and any plane-like or disk-like manifold into a disk. I don't think that this is true for general manifolds, but there are some results. I think there is a paper of Pfefferman about reconstructing manifolds from point clouds. So when you have a discrete version, a sampling of the manifold, under which assumptions you can recover the manifold against some heavy differential geometry that probably I don't understand to the full extent. So second part of the question, many representation learning approaches assume the embeddings lie on a unit hypersphere. So how restricting would the assumption be from a geometric perspective and in achieving desired equivariance invariance? And thanks for the great lecture. Thank you. So the unit hypersphere is just a form of normalization. So I think short answer, I don't know. I'm not sure that it is necessarily restricting. Yeah, I need to think about it. I don't have an immediate answer. So the first answer that I'm thinking, probably it will not be restrictive, but maybe I'm wrong. Yeah, I don't know.
I think this is probably the last question in the chairman at this moment, but probably we can still wait for a few seconds for the audience to type the question. So probably I can grab this chance to ask another question. So my question is, as you just mentioned, the computer vision community are so used to CNN, so probably they will not change to use their other network architecture. So as you know, toolkit is very important for to change the behavior of the researchers. So are there any useful toolkit for graph neural network?
Yeah, so there are multiple, probably the one that is used more in the research community is PyTorch geometric, so built for PyTorch. Another famous library that is now also supported and maintained by Amazon is DGL, Deep Graph Library. So mainly developed for TensorFlow. Yeah, and there are several others. And there are also separate libraries that are built for particular applications, such as dealing with molecular graphs, with proteins. So there is a graphene library that was developed especially for protein molecules. So there is a lot of things around. It's very different from what it used to be a couple of years ago.
We have one more question from the audience.
Yes, so Andrea is repeating his question about whether it was proven that it is better to use group equivariance than data augmentation. So the answer is yes. And then this was shown, for example, in the papers of Taco Cohen.
Okay. So I think we do not have further question. So, we have one more question. Probably we consider this as the last one.
Yeah, is there any solution for human activity recognition in unsupervised method by GNN? So I'm not sure what is meant by human activity recognition, but probably the intuitive answer I would give here, you're probably looking for some form of anomaly detection. So if you don't know a priori what is this behavior, but what you want to predict is whether it is different from the normal pattern, right? So it somehow stands out and breaks the normal pattern. So there are some works on anomaly detection using graph neural networks. I would suggest to look maybe in that direction.
Okay, so thank you very much, Professor Bronstein, to bring us an excellent lecture and bring us a happy ending for the lectures of Machine Learning Summer School. So thank you very much. Thank you. Thank you.
Thank you very much. It was a pleasure.
Thank you.